Hello there and welcome to Science for Sleep, where curiosity takes its time and science drifts softly between thought and dream. Tonight we're not just looking up at the night sky, we're reaching back through almost 14 billion years of cosmic memory, tracing the faintest whisper of light ever seen. The oldest light, in fact, that has ever reached our eyes. You can't see it directly. It's not the glow of a star or the shimmer of a galaxy. It's something deeper, quieter, older than all of them. A dim background hum that fills the universe evenly, stretching across every direction you look. Scientists call it the cosmic microwave background, but you might think of it as the universe's first photograph, taken long before there were cameras or stars or even atoms as we know them. Before we wander too far into that ancient light, I'd love to know, where are you listening from tonight? Is it quiet there? Maybe you're watching the last few lights outside your window fade, or hearing the low hum of distant traffic, or maybe just the rhythm of your own breath. Somewhere, far beyond this room, beyond the stars you can see, that same faint light is washing through space, passing gently through you, through me, through everything. It's been travelling since the dawn of time itself. If you find that thought soothing or strange or both at once, maybe give this little corner of calm a like or a follow. It helps more curious dreamers find their way here too. Now let's ease into the story, because this faint glow, this quiet cosmic background, is more than just light. It's evidence, it's history written in radiation. A time capsule from when the universe was just a few 100,000 years old. To understand it, we have to imagine a world so different from ours that it hardly seems real. A time when there were no galaxies, no stars, not even the faintest trace of a planet. Just a sea of heat and energy so dense that matter and light couldn't exist separately. The early universe was less like a place and more like an ocean of pure potential. And somewhere in that glowing chaos, the story of everything began. When scientists talk about the cosmic microwave background, they're really talking about what's left of the Big Bang. But the Big Bang itself wasn't an explosion that happened in one spot. It was space itself expanding, carrying everything with it. Imagine stretching a balloon with tiny dots on its surface. As the balloon grows, the dots move apart. That's how the universe expanded, not into something, but as something. Every point of space moved away from every other point. And in that first fraction of a second, everything we now know, all the galaxies, stars and atoms, was condensed into a form so hot and dense that it glowed brighter than anything we could ever imagine. That light, the light from the beginning, was everywhere. But as the universe expanded, it cooled. What was once a blinding fire began to dim. The glow stretched, the wavelengths of its light elongating as space itself stretched. Over billions of years, what began as an intense blaze in visible light shifted down the spectrum, becoming infrared, then microwave. Today, after nearly 13.8 billion years of cosmic expansion, that same ancient light is so faint it can only be detected by special instruments. Yet it still carries within it the imprint of the universe as it once was, a ghostly image of creation itself. It's strange to think that the most important picture in the history of everything isn't something we can see with our eyes. If you could somehow tune your television or radio to the right frequencies, some of the static you'd hear would actually come from that ancient radiation. The universe humming quietly in the background. That faint hiss, born before there were stars or even galaxies, fills every corner of the cosmos. It's everywhere you look, every direction you turn. Scientists sometimes call it isotropic, meaning the same all around, though it's not perfectly uniform. And those tiny variations, those tiny ripples of temperature, just millionths of a degree, would later become the seeds of everything in the universe, the places where matter would gather, where galaxies would form, and where, much later, beings like us would wonder how it all began. But let's not rush there yet. Let's stay in that early time for a while. even if only in imagination. The universe then was a hot, glowing plasma, filled with electrons, protons, and photons all colliding endlessly. It was opaque, because light couldn't travel far without being scattered. Every photon, every particle of light would bump into free electrons almost immediately, bouncing in random directions like light in a dense fog. The result was a universe without transparency, a cosmos wrapped in its own brightness, yet unable to let that brightness escape. To any hypothetical observer, and not that there were any, everything would look like a smooth, blinding glow. There was no up, no down, no edge, no sky, just endless radiance and heat. This might sound chaotic, but it was astonishingly orderly. Everything was nearly the same temperature everywhere, differing only by tiny fractions of a degree. It's one of the strangest facts about the universe's beginning, that it started so evenly, almost perfectly balanced. And yet those microscopic imperfections in that balance were crucial. Without them, there would be no structure, no galaxies, no stars, no planets. The universe would have remained a thin, uniform gas forever. Instead, those small differences became the blueprint for everything that followed. When cosmologists study the cosmic microwave background, they're not just looking at light. They're reading a fossil record of temperature variations, a map of the infant universe frozen in place after it became transparent. But before we get to that moment, the one when light could finally move freely, we have to understand what happened as the universe cooled. Because cooling was everything. In those first moments, the universe was unimaginably hot, billions of degrees. Particles and radiation existed in a kind of equilibrium, constantly colliding and exchanging energy. As it expanded, that energy spread out. The temperature dropped. After about 3 minutes, things had cooled enough for atomic nuclei to form, mostly hydrogen and helium with trace amounts of lithium. Still, there were no atoms as we know them, just nuclei and free electrons swimming through the hot plasma. It took hundreds of thousands of years more for the temperature to drop enough that electrons could finally bind with those nuclei to form neutral atoms. That event, called recombination, changed everything. Once electrons were bound into atoms, photons and particles of light no longer collided with them so easily. The fog lifted. Suddenly light could travel freely. For the first time in history, the universe became transparent. The light released at that moment has been travelling ever since, stretching and cooling as the universe expanded. What was once visible light has now become microwaves, cooled to just about 2.7 Kelvin above absolute zero. And that's the cosmic microwave background, the faint afterglow of creation, still shimmering softly across all of space. It's worth pausing on what that means. Every time we detect that radiation, we're receiving messages from a time before there were stars, before the first galaxies. We're looking back to when the universe was just 380,000 years old, a tiny fraction of its current age. It's the closest we can get to seeing the beginning with our own instruments. Beyond that moment, the universe was opaque. No light could travel from earlier times to reach us. In that sense, the CMB is like a cosmic horizon, the edge of the observable universe, the farthest point we can ever see. And yet, despite being ancient, it's everywhere around us. It passes through your body as you listen to this. Billions of photons from that primordial glow are streaming through you every second, unnoticed, harmless, constant. You are quite literally bathed in the afterglow of the universe's birth. There's something humbling in that, to know that even in the quietest room, even in sleep, you're surrounded by the faint echo of creation. When scientists first detected it in the 1960s, they didn't know what they had found. Two engineers, Arno Penzias and Robert Wilson, were testing a large radio antenna in New Jersey when they noticed a persistent background noise they couldn't explain. They tried everything to get rid of it. They checked their instruments, their circuits, even cleaned out what they politely described as pigeon residue from inside the antenna. but the hiss remained. It was coming from every direction, day and night, unchanging. Eventually, after comparing notes with cosmologists working nearby, they realised what it was. They had stumbled upon the echo of the Big Bang, the afterglow predicted by theory but never before observed. That discovery earned them the Nobel Prize, and more importantly, confirmed that the universe had a hot, dense beginning. Since then, our instruments have improved dramatically. Satellites like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, showing tiny variations in temperature and density across the sky. Those maps are not just pretty pictures, they're data-rich records of the early universe's structure, telling us about its age, composition, and even its shape. By studying the CMB, scientists can determine how fast the universe is expanding, how much dark matter and dark energy it contains, and how flat or curved space itself might be. All that from a faint glow less than 3 degrees above absolute zero. It's remarkable how much we've learned from something so subtle. If you were to stand outside on a clear night and somehow see microwaves with your eyes, the whole sky would shimmer faintly, evenly, with that background light. It wouldn't come from any single point. It would come from everywhere. The universe whispering softly in every direction. When you think about it, that makes the night sky even more beautiful. The stars we see are relatively young, mere latecomers in cosmic history. The real background, the ancient one, is still shining beneath them, invisible but ever-present. It's the oldest light we will ever see, and perhaps the most important. It tells us that the universe once burned bright and hot, that it expanded and cooled, and that we, billions of years later, can still catch the faint echo of that moment in our detectors and in our thoughts. The cosmic microwave background isn't just a relic. It's a reminder of how connected everything is across time. The photons that left that first transparent universe have been moving ever since, untouched and unbroken, crossing billions of light years to arrive here. When they were released, there were no stars, no galaxies, no Earth. And yet, they've travelled patiently through all the ages to meet our instruments, our minds, our curiosity. If you look closely at the data, you'll see that the CMB isn't perfectly smooth. There are minute temperature variations, warmer and cooler patches, just a few parts in 100,000. Those tiny differences are the fingerprints of quantum fluctuations, magnified by cosmic inflation, the incredibly rapid expansion that took place in the first instant after the Big Bang. They show where matter was ever so slightly denser, where gravity would later pull more strongly, gathering hydrogen into the first stars and galaxies. In that sense, the CMB is not just the universe's first image, but also its first blueprint. When the first light began to drift freely through space, the universe was still unimaginably young. That faint glow we now call the cosmic microwave background had just been released, but in that moment, the cosmos was only beginning to wake. It was a slow awakening, quiet, patient, and vast beyond comprehension. For hundreds of thousands of years before that, the universe had existed as a blinding fog of energy and plasma, where no single beam of light could travel far without scattering. But now transparency had arrived. Light could move freely, and with it came something new, the possibility of structure. The fog had lifted, and the universe, in a sense, opened its eyes for the first time. If you could somehow stand in that newborn cosmos, you wouldn't see stars or galaxies yet. The darkness we associate with space hadn't appeared. Instead, the entire sky would still glow with a warm amber light, fading gradually as the universe continued to expand and cool. There was no direction, no constellations, no up or down. Every point in space looked the same, filled with soft, radiant brightness. It was peaceful, though not in any human sense. There were no observers, no thought, no sound. Only the slow, silent cooling of everything that would one day become something. The energy of the early universe was astonishing. Just a few 100,000 years earlier, everything had been tightly packed and furiously hot. A fireball so dense that space itself carried more energy than matter. As it expanded, that energy began to thin out, allowing particles to slow down enough to combine. The physics of that transformation is precise and elegant. Protons, the positively charged particles in atomic nuclei, finally captured electrons, the negatively charged particles that had been darting freely through the plasma. With those electrons bound, the radiation that once scattered endlessly could now travel in straight lines. That was the turning point, the transition from a universe of light trapped within itself to a universe of light set free. What followed was a cosmic cooling. As the universe expanded, the temperature continued to drop. From billions of degrees in its earliest moments, it fell to just a few thousand. At that point, light no longer carried enough energy to break apart atoms, and the glow that filled everything began to dim. Space stretched, wavelengths of radiation elongated, colours shifted. What had once been a brilliant white blaze faded to deep red, then to infrared, and eventually, over billions of years, to the microwave radiation we now detect. The light didn't disappear, it just changed its tune. The melody of creation slowed into a gentle hum. This quiet transformation marks the true beginning of what we think of as the universe. Before then, it was a sea of energy. Afterward, it became a place where matter could gather, where gravity could start to do its slow, relentless work. That work would take millions of years to show its first results, but the process had begun. The universe was no longer just expanding, it was evolving. One of the most striking things about this period is how uniform everything was. The temperature, density, and distribution of matter were almost perfectly balanced, differing by less than 1 part in 100,000. You might think such smoothness would mean stillness, but in fact it was the tiny imperfections that mattered most. Those minute differences, invisible on any human scale, became the seeds of cosmic structure. Slightly denser regions pulled in more matter under gravity, and over time, that extra mass made them even denser still. It was the start of a slow chain reaction that would eventually lead to stars, galaxies, clusters, and everything else that dots the night sky. The smoothness of the early universe made it stable, but the tiny ripples within it made it alive. Imagine the sound of that early cosmos if it could be heard. Not the sharp noise of explosions, but a low, resonant hum. Scientists call these acoustic oscillations, pressure waves that rippled through the plasma of the young universe before it became transparent. Those ripples froze in place when light was released, leaving their imprints on the cosmic microwave background. We can still detect those subtle variations today as faint differences in temperature, and they tell us about the sound waves that once echoed through that primordial sea. In a sense, the universe began not just with light, but with sound, a deep, steady rhythm woven into space itself. Once the fog cleared, the universe entered a long period that cosmologists sometimes call the Dark Ages. Despite the name, it wasn't a time of chaos, but of waiting. There was light, but it was stretched to longer and longer wavelengths, growing weaker with every passing million years. Space itself expanded faster than gravity could gather matter together. Hydrogen and helium atoms drifted quietly, unilluminated, spread thinly across the cosmos. There were no stars yet to ignite, no galaxies to shine, only the faint cooling afterglow of the Big Bang filling the void. During these long ages, gravity worked in silence. Slowly, patiently, it began to draw gas toward the slightly denser regions marked in the cosmic microwave background. It's almost impossible to grasp the scale of time involved. The first stars wouldn't appear until about 100 to 200 million years after the Big Bang. For all that time, the universe existed in semi-darkness, filled with invisible radiation and drifting clouds of gas. and yet even then the blueprint of everything to come was already written in the faint temperature ripples of that first light. If you were to look at those ripples on a map, you'd see patterns that tell us not just what the universe looked like then, but how it would grow. Slightly denser patches became the seeds of galaxies. Slightly cooler areas marked regions of less matter, the spaces between the great cosmic structures. The CMB is a snapshot of that balance, a record of the earliest contrast between matter and emptiness, between what would become something and what would remain void. In the decades since it was first discovered, scientists have used that faint pattern to measure some of the most fundamental properties of the universe. Its age, its composition, its rate of expansion, all can be inferred by studying how the cosmic microwave background varies across the sky. What's more, those variations match perfectly with the predictions made by the Big Bang Theory, confirming it beyond reasonable doubt. Every piece of evidence points to one conclusion, that the universe began hot, dense and uniform, then expanded and cooled into the complex cosmos we see today. But at this stage of its history, complexity hadn't yet arrived. The young universe was simple, filled mostly with hydrogen, a little helium, and traces of other light elements. It was vast but empty in the way a field can be empty before the grass grows. It had the potential for everything, but almost nothing had yet taken shape, and still, that faint background radiation continued to travel, undisturbed, stretching with space, filling it evenly, serving as both the light of dawn and the quiet witness of everything that would come after. It's humbling to realize that the light we detect today from that era has been traveling almost the entire age of the universe. Each photon from the cosmic microwave background has crossed billions of light years, avoiding collisions, passing through the formation of galaxies, the birth and death of stars, the rise of planets, and eventually arriving here to the detectors that would record its faint signal. When we measure the CMB, we are quite literally catching ancient light in our hands, light that began its journey when the universe first learned to let go of its own brightness. That moment of release, when the fog cleared, was one of transformation. Before it, the universe was dominated by radiation. After it, matter took over. The energy density of light fell faster than that of matter as the universe expanded, and so gravity began to gain influence. For the first time, the pull of matter could start to shape the large-scale structure of the cosmos. The universe, in a sense, began to organize itself. The seeds sown in the microwave background started to grow, though the process would take eons. During this long awakening, the universe's expansion continued steadily. Galaxies were still far in the future, but the framework for them was being drawn by the invisible hand of gravity. Hydrogen atoms collided and clumped, slowly forming denser pockets of gas. Within those pockets, pressure and temperature increased. Eventually, these regions would collapse under their own gravity to ignite the first stars, but that's still far ahead in our story. For now, the universe was simply stretching, cooling, and waiting, like a vast breath held between moments. From a scientific standpoint, this period is one of remarkable simplicity. The equations that describe it are elegant and precise. We can model how photons decoupled from matter, how they redshifted as space expanded, and how tiny density fluctuations evolved under gravity. But beyond the numbers lies something even more profound, the recognition that this was the universe's first act of clarity. Before this, everything was hidden in light too bright to see. Afterward, the universe could finally observe itself, not through eyes, but through the free motion of light. Transparency is a quiet revolution. You can think of it almost like the first morning after an endless storm. For hundreds of thousands of years, energy had filled every corner of existence, battering particles into chaos. Then, slowly, the storm eased. The clouds began to part and light, for the first time, could travel unhindered. That light has never stopped travelling. It's still moving now, still expanding with space, Its wavelength stretched thousands of times longer than it began. It has cooled from thousands of degrees to less than 3 above absolute zero, and yet it still carries the same story, the same memory of that first calm after chaos. When you look at the modern universe, the galaxies, the stars, the planets, and the space between, it's easy to forget that all of it comes from the faint patterns frozen into that background light. Those patterns are the fingerprints of creation. They tell us not just that the universe had a beginning, but that it woke up gently, following laws so consistent that we can still trace them billions of years later. The story of the cosmic microwave background isn't one of sudden explosions or dramatic endings. It's a story of gradual transformation, of heat turning into structure, of energy cooling into matter, and of light slowly learning to wander free. And that wandering light, those photons from the dawn, are what make it possible for us to see the universe at all. Every telescope, every camera, every pair of eyes that's ever gazed upward depends on the same principle that began then: light moving freely through space. Before recombination, that wasn't possible. After it, the universe became transparent forever. In a sense, the cosmic microwave background didn't just illuminate the cosmos, it gave it vision. Even now, when astronomers study that light, they see subtle clues about what happened in those early days. The exact patterns of temperature and polarization reveal not only how matter was distributed, but how space itself was shaped. Tiny ripples in the CMB can tell us whether the universe is flat or curved, how much dark matter it contains, and how quickly it's expanding. From that faint afterglow, we can reconstruct almost the entire cosmic history. That's the power of the first light. It carries everything that came after hidden within its details. So when we say the universe woke up, it wasn't a single moment, but a gradual unfolding. The fog lifted, the light escaped, gravity began its slow choreography, and the cosmos started to take form. It's still waking in a way. Stars are still being born, galaxies still colliding, and somewhere out there, light is still stretching, cooling, whispering through the void. The same light that first escaped nearly 14 billion years ago still surrounds us. The universe never truly stopped glowing. It just learned to glow quietly. Before there was calm light drifting through transparent space, before atoms found their places and the first stars began to form, there was only heat. The universe, still impossibly young, existed as a restless sea of energy and matter, thick and bright and constantly shifting. Everything we know today, every atom in your body, every grain of sand, every distant star was once part of that ocean. Not arranged or structured, but swirling together in a state so dense that the distinction between matter and radiation barely existed. It wasn't chaos in the sense of confusion. It was order at its most extreme. A perfect balance of collisions, interactions, and transformations happening everywhere at once. When cosmologists look back on this early phase, they often describe it as a plasma, a hot soup of particles and light where electrons, protons, and photons moved in a constant dance of creation and destruction. Every time a proton tried to capture an electron to form an atom, a photon of light would crash into it and knock it apart again. The result was a universe that glowed with tremendous brightness, but could not let any of that light escape. Every photon, every particle of radiation, was trapped by the density of matter. The cosmos was luminous but blind, radiant but opaque, filled with light that could not travel. If you could somehow step into that era, which of course you couldn't, because nothing solid or human could survive there, the view would be strange beyond imagining. The universe had no empty space, no stars, no points of darkness. It was filled completely, everywhere, with light bouncing from particle to particle. Every direction looked the same. There was no horizon to look toward, no boundary to step beyond. Temperature and brightness extended infinitely, smooth and even. The concept of distance itself was different. Space was expanding, but there were no landmarks yet to measure that expansion against. In the earliest moments after the Big Bang, the universe was so dense that even the fundamental forces behaved differently. The electromagnetic force, the weak and strong nuclear forces, and gravity were all tangled together in a state of symmetry. As the universe expanded and cooled, these forces began to separate, each taking on its distinct character. It was the first phase transition, the first sorting of reality into the patterns that would later define it. The cooling wasn't fast in any human sense. It unfolded over hundreds of thousands of years, but it was steady. The temperature dropped, particle by particle, until conditions changed enough for matter and radiation to go their separate ways. This separation was inevitable. Physics doesn't allow perfect balance to last forever. Even in the most uniform systems, tiny fluctuations appear, quantum variations that, on a microscopic level, cause differences in density. In that early sea of plasma, these fluctuations were minuscule, far smaller than anything we could ever perceive directly. But because the universe was still small and everything interacted with everything else, those small differences mattered. They grew slowly, almost imperceptibly, as gravity began to tug slightly more strongly in some regions than in others. What started as quantum uncertainty became the seeds of cosmic structure. Before those seeds could grow, though, the universe had to pass through this long, bright adolescence, a period when photons and particles were still bound together in a dance that would last until the moment of decoupling, the time when light finally escaped. During this plasma era, space was filled with an interplay between radiation pressure and gravity. Radiation tried to push outward, keeping matter spread evenly. Gravity tried to pull inward, gathering it together. These opposing forces created oscillations, tiny compressions and rarefactions that rippled through the plasma like sound waves through air. Those ripples are still visible today in the patterns of the cosmic microwave background. When you see a map of the CMB with its blue and red patches, those are the echoes of that ancient pressure wave, frozen sound from a time before there were ears to hear it. It's almost poetic to think that the first rhythm the universe ever produced wasn't mechanical or biological, but physical, a vibration of space itself. These acoustic oscillations reveal a lot about the conditions of the early cosmos. Their scale tells us how fast the universe was expanding. Their amplitude tells us how much matter it contained. Every detail in that pattern is a clue, a fossilized trace of a time when everything was still molten and radiant. The temperature back then was extraordinary, around 10,000 degrees Kelvin and falling. At that heat, atoms couldn't survive. Photons carried enough energy to tear apart anything that tried to bind. The radiation pressure kept matter ionized, meaning electrons remained free, unattached to nuclei. Every few centimeters, a photon would collide with an electron changing direction. It was this constant scattering that made the universe opaque. You could think of it like sunlight in a dense fog, except the fog itself was made of light. Nothing could travel far without bouncing, and every bounce carried energy across space in all directions, keeping the temperature nearly uniform. Despite that uniformity, this sea of fire and fog wasn't static. The expansion of the universe stretched everything, cooling it slowly but steadily. Over vast scales, space grew, wavelengths of light lengthened, and density decreased. With each expansion, the particles had slightly more room to move. Collisions became less frequent. The cosmic fog began to thin, though it would take hundreds of thousands of years before light could finally break free. During this long phase, matter and radiation were deeply intertwined. The energy density of the universe was dominated by radiation, not matter. This meant that light essentially controlled the expansion rate. Gravity pulled inward, but the sheer pressure of radiation pushed outward just as powerfully. In the balance between those two, the geometry of the universe was set. That balance determined whether the cosmos would expand forever, collapse back on itself, or hover delicately on the edge of equilibrium. As it turns out, the universe came remarkably close to perfect balance. So close that even today we measure its curvature as almost exactly flat. That flatness was established in this glowing era, written into the very shape of space while everything was still too hot to see. The notion of flatness can be difficult to imagine. It doesn't mean the universe is two-dimensional or pancake-shaped. It means that, on the larger scales, parallel lines never converge or diverge, and the rules of geometry remain consistent across billions of light years. That property is one of the great mysteries of cosmology, and it traces back to the same plasma that filled space in these early moments. From this fog of energy, the structure of the universe's future was already imprinted. As we trace that history, it's striking how everything depends on temperature. At the highest temperatures, even fundamental particles couldn't exist in stable form. As cooling progressed, quarks combined into protons and neutrons. Later, those protons and neutrons fused into the first atomic nuclei during a period called nucleosynthesis. But it wasn't until the universe cooled enough for electrons to settle into orbits around those nuclei that true atoms could exist. That stage, the one we often call recombination, marked the end of this fiery fog. Until then, though, the universe was defined by collision, constant interaction, endless transformation. Imagine that sea of particles, every photon a packet of light energy, every proton an electron a fragment of matter, all engaged in ceaseless motion. It's hard to find an analogy for something so complete. Perhaps the closest we come in everyday life is looking into the core of a star, though even that comparison falls short. Stars are structured, layered, and small compared to the cosmos. The early universe was uniform without boundaries. The plasma that filled it wasn't contained, it was everything. And within that everything, physics played out with exquisite precision. Every particle obeyed the same laws everywhere. The speed of light, the strength of gravity, the behaviour of electromagnetism, all constant, all perfectly tuned. That consistency allowed the universe to evolve coherently, to cool evenly, and to make the transition from radiation to matter domination without tearing itself apart. You could say this was the universe's formative period, when it learned its own rules. The same constants and interactions that define the behaviour of atoms today were already operating then. Quantum mechanics governed the microscopic fluctuations. Thermodynamics described the flow of energy. General relativity dictated the curvature of space-time. From the very beginning, the laws of physics were not invented, they were expressed. And those expressions shaped everything that followed. One of the reasons scientists study the cosmic microwave background so carefully is that it preserves the fingerprint of this plasma state. Every tiny variation in the CMB's temperature tells us something about how the universe behaved when it was still a sea of fire. When we map those variations, we're essentially mapping the ripples frozen into that early fog. The warm spots are regions where matter was slightly denser. The cool spots show where it was slightly thinner. From those subtle differences, we can infer how sound waves moved, how fast the universe expanded, and how gravity began to sculpt structure from uniformity. Over time, as the universe continued to cool, the scale of these fluctuations set the pattern for everything that would come after. The densest regions became the first gravitational wells, pulling gas inward. The less dense regions expanded more quickly, forming the vast voids we now see between galaxy clusters. The cosmic web, the large-scale pattern of filaments and gaps that stretches across billions of light years, has its origins right here, in this plasma phase, in those faint ripples of density that first appeared when the universe was still a fog of light. It's remarkable that such small differences could lead to such dramatic consequences. The difference in temperature between one region and another was only about 1 part in 100,000. Yet over billions of years, gravity amplified those differences until they became stars and galaxies, clusters and superclusters. It's a reminder that in the universe, small things matter deeply. Tiny irregularities in an otherwise perfect system can be the seeds of everything. The physics of this process can be described with precision, but the emotional weight of it is harder to capture. To realize that the night sky, every glittering star, every glowing nebula, owes its existence to microscopic fluctuations in a sea of plasma billions of years ago is almost too vast a thought to hold. It means that structure, complexity, and even consciousness trace back to that moment when light and matter were one and the same. The fog we could not see through is, in a sense, the ancestor of sight itself. Eventually the balance tipped. The universe cooled below the critical temperature, and the constant collisions that define this era began to fade. Photons no longer had enough energy to strip electrons from atoms, and matter began to take stable form. The sea of fire thinned into transparency. For the first time, light could travel unimpeded. That light, those photons, are the very ones we now detect as the cosmic microwave background. They have been on their journey ever since, carrying within them the record of that transformation. It's almost serene to think that what was once blinding fire has become the softest glow imaginable, stretched by expansion into gentle microwaves that fill the sky. In that sense, the universe has never stopped glowing. It has simply aged gracefully. The fire became fog, the fog became transparency, and transparency became the silent background against which all things unfold. As we move forward in this story, that transition from heat to light, from opacity to clarity, marks the beginning of everything that followed. The sea of fire and fog was both an ending and a beginning. It was the last moment before the universe became visible, and the first moment of everything that would one day shine on its own. And as that light continued its slow, endless journey outward, the cosmos entered a new age. Gravity began to weave the first patterns. The darkness deepened, and in it the seeds of stars waited quietly for their time to ignite. The fog was lifting, slowly, quietly, almost imperceptibly. The universe was changing from a blinding ocean of plasma into something clear. For the first few 100,000 years, everything had been too hot for atoms to exist. The constant collisions between photons and electrons kept everything ionized, every attempt at structure immediately undone by the intensity of light itself. But expansion was patient. With every passing moment, the universe stretched a little further, cooled a little more, and drifted toward a threshold. When the temperature finally dropped to around 3,000 degrees Kelvin, something remarkable happened. The light that had been trapped for so long was set free. In that instant, the universe became transparent. It's hard to picture what transparency means on a cosmic scale. Before this moment, photons, the particles of light, couldn't move more than a few millimeters before being scattered by electrons. Space was bright but impenetrable, as though wrapped in endless cloud. Then, in a span of just a few thousand years, those electrons combined with protons to form neutral hydrogen atoms. The collision stopped. Light could move unhindered. The universe, for the first time, became visible to itself. This event is known in cosmology as recombination, though that word doesn't quite capture its simplicity. There was no previous combination to redo. It was the first time electrons and nuclei had ever joined permanently. But the term stuck because it describes the binding of charged particles into neutral atoms. Once that happened, photons no longer interacted so strongly with matter. The great cosmic fog that had filled everything for hundreds of thousands of years finally cleared. If you could have witnessed it, the transformation would not have been sudden or dramatic. There would have been no flash, no sound, no boundary sweeping across the cosmos. It would have been a gradual fading, like the slow clearing of mist under a rising sun. The glow that had filled the universe softened as light began to travel freely. What had been a uniform blaze became a diffuse radiance, cooling with every expansion of space. That light is still travelling today, stretched by billions of years of cosmic growth, its once golden wavelength now elongated into the microwaves that wash over every inch of the sky. It's strange to think that the light we detect in the cosmic microwave background isn't light from stars or galaxies, but from the very first time light could move. It's the oldest light that can ever reach us, because anything before that moment is hidden behind the fog of the plasma era. No telescope, no matter how advanced, can see further back than this. The surface from which that first light escaped is sometimes called the last scattering surface, not because it's a physical wall, but because beyond it, scattering was constant and total. It is, in effect, the universe's first visible horizon, a curtain of light stretching across all directions. Every photon that makes up the cosmic microwave background has travelled through space since that moment, a journey of nearly 13.8 billion years. During that time, the universe has expanded more than 1,000-fold. Those photons have been redshifted from visible light into microwaves, cooled from thousands of degrees to just 2.7 above absolute zero. Yet they still carry the faint imprints of the conditions in that early universe. The temperature variations, the density fluctuations, the signatures of the very first structures. Each photon is like a messenger from the dawn, arriving here after a voyage that has lasted the entire age of the cosmos. Recombination marks a turning point not just in the history of light, but in the history of matter. Before it, radiation dominated. Photons carried most of the energy in the universe and controlled its expansion. Afterward, matter took over. The energy density of radiation fell faster than that of matter as the universe stretched, and gravity began to assert itself more strongly. The cosmos entered a new era, one defined by the slow gathering of gas into clouds, by the silent choreography of gravitational attraction. The light had gone free, but matter was now beginning to settle. In that balance between release and gathering lies much of what makes the universe the way it is. The photons that escaped continued outward, painting the cosmos with a faint uniform glow. The atoms that remained began to cool further, drifting gently through space, influenced only by gravity and the small irregularities frozen into the density field. Those irregularities, so tiny they might seem inconsequential, were amplified over time. Slightly denser regions attracted more matter, becoming denser still. Slightly emptier regions became more empty. It was a feedback loop written into the laws of physics, and from it, the first structures would eventually emerge. To understand how precisely this transition unfolded, scientists study the cosmic microwave background in extraordinary detail. The CMB isn't perfectly smooth. It contains fluctuations in temperature of only a few tens of millionths of a degree. These differences tell us everything about the conditions during recombination, the density of matter, the rate of expansion, even the proportions of ordinary matter, dark matter, and radiation. When mapped across the sky, these tiny variations create a speckled pattern that looks almost random but isn't. It's the statistical fingerprint of the early universe, the first readable page in the cosmic record. Satellites like COBE, WS-MAP, and Planck have refined our view of that record to exquisite precision. They've shown that the universe at the moment of recombination was astonishingly uniform, with just enough unevenness to allow structure to grow. Those observations have confirmed the Big Bang model beyond any reasonable doubt, but they've also revealed subtler details, like the fact that the universe appears to be spatially flat, meaning its overall geometry isn't curved significantly by gravity. That insight, drawn from the pattern of fluctuations in the CMB, tells us something profound about the universe's earliest moments, long before recombination itself. But for now, it's enough to stay in that moment of transition, when the universe first became clear. The concept of clarity might sound simple, yet on this scale it's monumental. It means that for the first time, information could travel freely across vast distances. Light could move in straight lines, carrying with it an imprint of where it had come from. That ability to carry information is what makes observation possible at all. From this moment onward, the universe began leaving traces, signals, patterns, radiation that could later be measured and interpreted. Before recombination, everything was hidden behind the fog of scattering. After it, the universe became legible. You could think of it as the moment when the cosmos first began to remember itself. Every photon of the CMB is a record, an unbroken link between then and now. It tells us how dense the universe was, how fast it was expanding, and how smooth or lumpy it appeared on the larger scales. When scientists measure these photons today, they're effectively looking back through time, decoding the conditions of that first moment of transparency. It's remarkable how well we can reconstruct those conditions. The physics of recombination is precise enough that we can calculate when it occurred, about 380,000 years after the Big Bang. We can estimate the temperature at which atoms formed, the density of hydrogen and helium, even the fraction of photons that escaped in different directions. These numbers come not from speculation, but from measurements of the CMB's frequency spectrum and angular power distribution. In other words, the universe has left behind a perfect data set, and it began forming the moment clarity arrived. Still, for all the precision, there's something profoundly quiet about this stage of history. The blazing energy of the first few minutes had faded. The violent collisions of the plasma era were over. No stars had yet ignited. There were no galaxies, no black holes, no heavy elements, just neutral hydrogen and helium gas expanding slowly into the deepening dark. The cosmic background radiation filled every direction equally, a soft uniform glow now beyond the reach of any eye. In that sense, the universe had entered a calm between storms, the calm before the birth of the first stars. The passage from opacity to transparency also changed the way gravity worked on large scales. When matter was coupled to radiation, the pressure of light resisted collapse. Regions that tried to grow denser would be pushed outward by the pressure of trapped photons. Once light escaped, that counterpressure vanished. Gravity could now operate unhindered, allowing matter to clump together more efficiently. The transition from a radiation-dominated to a matter-dominated universe was not just a change in energy balance, it was a shift in how structure could form. The slow gathering that began then is still continuing today, billions of years later, as galaxies cluster and superclusters form. It's humbling to realise that the light released at recombination hasn't stopped travelling since. Every photon continues outward in all directions, tracing an ever-expanding sphere around its point of origin. Because the universe itself is expanding, that sphere is now unimaginably large, tens of billions of light-years in radius. We, standing here, are inside one such sphere, receiving photons that were emitted from every direction of space at that same early moment. Every point in the universe sees its own version of the cosmic microwave background, centered on itself. In that way, every observer, no matter where they are, occupies the center of their own observable universe. There's a quiet symmetry in that. The cosmos has no single center, no privileged point from which it expands. Every region of space looks the same on the larger scales. Every observer sees the same faint background. Every photon carries the same story. It's as though the universe, from the very beginning, was designed to be democratic, to give every place the same view of its own past. When scientists build detectors to measure this ancient light, they're doing more than taking a picture. They're listening to a conversation that began nearly 14 billion years ago. The faint microwaves they collect are the final words of the early universe's first sentence. From those words, we've learned not just when the fog lifted, but what the fog was made of, how it behaved, and what it left behind. Even now, the cosmic microwave background isn't perfectly static. As it passes through clusters of galaxies, it can be slightly distorted by gravitational lensing or by the scattering of electrons in hot gas. These secondary effects allow scientists to trace the distribution of matter in the more recent universe. In this way, the light from recombination continues to inform us, not just about the past, but about everything that has happened since. It's both a relic and a tool, ancient and alive in its usefulness. If you could see the CMB with your eyes, it wouldn't look bright. It would be invisible, its wavelength far too long for human vision. But if you could somehow translate it into visible colours, the sky would glow evenly with a soft, diffuse warmth, the same in every direction. The stars we see would appear as small interruptions against that background, temporary points of brightness overlaid on an eternal field. The background itself, though faint, would be the truest image of the universe as a whole, a snapshot not of a place, but of a condition. This first moment of clarity didn't just allow light to travel, it set the stage for the birth of time as we experience it. Before transparency, the universe was too uniform for events to have distinct separations. Every point was like every other, every moment the same as the last. Once light could move freely, differences could persist, causality could stretch across space, and distinct regions could evolve independently. The unfolding of cosmic history, the formation of stars, galaxies, and worlds, depended on this newfound ability for information to cross distances without being erased. You could say that clarity made memory possible, and memory made evolution possible. From this moment on, the universe would accumulate structure and change. The radiation that had once trapped everything would become the background hum against which all future events took place. Light would still dominate the universe, but in a different way, as illumination, not confinement. It's remarkable that this simple physical process, electrons joining protons to form neutral atoms, should have such profound consequences. It's a reminder of how often the universe changes not through violent cataclysm, but through quiet transitions. There was no explosion at this stage, no sudden rupture, just cooling, expansion, and the slow emergence of transparency. Yet out of that quiet came everything we can see. If the earlier universe was a storm of brightness, this was the clearing sky. Light, no longer trapped, began its journey outward. Matter, no longer buffeted by radiation, began to gather. Space, no longer opaque, became the canvas for everything that would later shine upon it. From this balance of freedom and attraction came the universe we inhabit now, a place where light can move, matter can form, and consciousness can one day look back and understand. The moment of clarity, then, wasn't a single instant, but a transition that changed the character of everything. It was the point where the universe shifted from being a glowing fog to being a transparent expanse. The same physical laws applied before and after, but their consequences were utterly different. Before, the universe was too dense for light to reveal it. After, it could be seen, measured, and eventually known. That light, still travelling, still cooling, still stretching with the expansion of space, continues to whisper across the cosmos. Every photon that reaches us carries a memory of that first dawn, and as we study that ancient glow, we are in a way still standing within it, still bathed in the first clarity the universe ever knew, and so the light continued on its endless path, while the gas it left behind began to drift and gather. In the growing calm after the fog lifted, gravity prepared its next great act, the shaping of matter into the first true structures. The stage was set for darkness to take hold, and within that darkness the first sparks would one day ignite. The light that first escaped into the universe has never stopped travelling. It's older than every star, older than every galaxy, older than the very atoms that make up most of what we see now. When we talk about the cosmic microwave background, we're talking about the oldest light in the sky, not the light of something burning, but the faded afterglow of something cooling. It isn't a light you can see, not with your eyes or a telescope that collects visible waves, but it's there, surrounding you at this moment. It moves through you, through the walls of your room, through the earth itself, quiet and constant, a soft echo from when everything began. The light was released nearly 14 billion years ago, when the universe was just beginning to clear from its dense fog. Back then, it was visible, bright enough to bathe the entire cosmos in a warm amber glow. As space expanded, the light stretched, its wavelengths elongating. The expansion of the universe doesn't just move galaxies apart, it literally stretches the light travelling through it. What began as visible light has now stretched thousands of times longer, transformed into microwaves. That stretching means the light has cooled as well, dropping from a temperature of around 3000 degrees Kelvin to just under 3. It's a change not of the light's nature, but of its scale, and that's what allows us to see into the past simply by detecting its faint, lingering warmth. To find that light, scientists don't look through telescopes pointed at stars. They build instruments sensitive enough to pick up the faint hiss of radiation spread evenly across the entire sky. The first time this radiation was measured, it was by accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna in New Jersey. They were trying to eliminate background noise from their experiments, but no matter what they did, a persistent static remained. It didn't change when they pointed the antenna in different directions. It didn't fade with the seasons or the day. It was everywhere, unchanging, as though coming equally from every part of the sky. They thought it was interference. They even cleaned out pigeon droppings from inside the antenna, thinking that might be the cause. But the hiss persisted. At the same time, a few miles away, a team of physicists at Princeton was working on a theoretical prediction that if the universe began in a hot, dense state, there should still be residual radiation filling all of space. When Penzias and Wilson learned of this, the realization clicked. The noise wasn't interference, it was the sound of the universe itself, the first light stretched and cooled by time. What they had found, quite literally, was the echo of the Big Bang. That discovery, made by accident, became one of the most important pieces of evidence in all of cosmology. It confirmed that the universe had a beginning and that it evolved from an earlier, hotter state. Today, we can detect that same light with far greater precision. Instruments like COBE, WMAP, and the Planck satellite have mapped the sky in microwaves, revealing that the background radiation is astonishingly uniform, the same in every direction to 1 part in 100,000. It's almost perfectly smooth, yet those tiny imperfections are crucial. They mark the places where matter was slightly denser in the early universe, where gravity would later gather material to form the first galaxies. The map of the CMB is, in a sense, the blueprint of cosmic structure, the first pattern ever imprinted on space itself. It's hard to overstate what this means. When we look at the cosmic microwave background, we're not just seeing back in time, we're seeing the limit of sight itself. The CMB marks the boundary between what can and cannot be observed, because before that light was released, the universe was opaque. No radiation from earlier times can reach us. It's like a fogged window into the beginning. We can see the surface of the fog where it cleared, but not what lies behind it. That surface exists in every direction, forming a sphere around us at a distance of about 46 billion light years. It's not that the light has travelled for 46 billion years. The expansion of space has stretched the distance during its journey, but in every direction we look, the same faint glow waits, the same relic of the same moment. This symmetry is one of the most extraordinary facts about the cosmos. No matter where you are in the universe, if you could detect microwaves with perfect sensitivity, you'd see this same glow, almost identical in every direction. Every observer, no matter their location, sees themselves at the centre of their own cosmic sphere of light. That's not because there's a true centre, but because space itself expands evenly. The CMB wraps every point in the universe equally, a silent reminder that we all share the same origin. The radiation's uniformity was one of the first great mysteries of cosmology. How could regions of the sky separated by billions of light years have the same temperature, when there hadn't been enough time for light to travel between them and even out the differences? This question, known as the horizon problem, eventually led scientists to propose the idea of cosmic inflation, a brief, incredibly rapid expansion in the universe's earliest fraction of a second. During inflation, regions that were once close enough to interact were suddenly pushed far apart, explaining why they still share the same temperature and properties. The CMB is, in that sense, a fossil imprint of inflation's aftermath. Its smoothness tells us how uniform the early universe was. Its small fluctuations tell us how inflation seeded the structure that would grow later. Each tiny temperature variation in the CMB corresponds to a slight difference in density in the early plasma. Over time, those differences grew. Denser regions attracted more matter, forming the seeds of galaxies and clusters. Less dense regions became the vast voids that fill most of the universe's volume. The cosmic web, the vast structure of filaments and gaps that we see stretching across billions of light years, all began with these faint ripples frozen into the background light. When scientists study the CMB, they're studying the origin of structure itself, the earliest trace of the pattern that would one day give rise to everything we see. The precision with which we can now measure this ancient light is astonishing. The Planck satellite, for instance, mapped the CMB with an accuracy of microkelvins, millionths of a degree. Those measurements have allowed cosmologists to determine not only the universe's age, but also its composition. From the CMB, we know that about 5% of the universe is ordinary matter, the stuff that makes up atoms, stars and planets. About 27% is dark matter, an invisible substance that interacts through gravity but not light. And about 68% is dark energy, the mysterious force driving the universe's accelerated expansion. These numbers come directly from analysing that faint background glow, from teasing out its subtle variations and comparing them with the predictions of theory. When you think about it, the fact that we can measure the entire history and content of the universe from a faint radiation that fills the sky is extraordinary. The CMB isn't bright. Its intensity is equivalent to just a few hundred photons per cubic centimetre, a whisper of energy, colder than the coldest vacuum we can make in laboratories. Yet hidden within that whisper is a complete record of the cosmos's birth and evolution. It's the closest thing to a photograph of creation we'll ever have. If you could somehow tune your senses to perceive it, the world around you would look different. Instead of darkness between stars, you'd see a soft, diffuse glow, even and constant, filling all of space. It wouldn't cast shadows or flicker. It would simply be there, silent, steady, as it has been since the beginning. Every star and galaxy would seem to float within that pale background, each one a small variation upon a much older light. This CMB is not static in the strictest sense. As the universe expands, it continues to cool. In another few billion years, its temperature will fall even further, from 2.7 Kelvin to perhaps 2.5, then 2.3, and so on. Eventually, as the universe grows older and emptier, the CMB will become even fainter, its wavelength stretched into longer and longer radio waves until it fades beyond detectability. The universe will never lose that light, but it will stretch until it becomes invisible to any conceivable observer. What we see now, then, is a fleeting moment in cosmic time, an era when the first light is still bright enough for us to detect, but ancient enough to carry the full memory of the beginning. Even though it's everywhere, we don't feel it. The photons that make up the CMB are too low in energy to have any noticeable effect. They pass through our bodies without resistance, through the air, through rock, through entire planets. They don't heat or illuminate, they just move on as they always have. Billions of them pass through you every second unnoticed. You are quite literally bathed in the oldest light in the universe, whether you're aware of it or not. Sometimes, when you tune an old television to static, a small fraction of that noise comes from the CMB. The rest is interference from our own atmosphere and electronics, but a trace of that hiss, that speckled fuzz of light and dark, is the direct signal of those ancient photons. It's a strange thought, that the static on a screen might be a faint echo of creation, captured accidentally by a household device. It's a reminder that the universe's history isn't remote or unreachable. It's all around us, woven into the invisible radiation that fills every corner of space. The CMB also carries clues about something even more subtle: the shape of the universe itself. The way the temperature fluctuations appear across the sky depends on the curvature of space. If the universe were closed, like the surface of a sphere, those patterns would look different than if it were open, like a saddle. Precise measurements show that the universe is remarkably flat, meaning that on the larger scales geometry follows Euclidean rules. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees. That flatness tells us that the density of the universe is very close to a critical value, the balance point between eternal expansion and eventual collapse. The fact that the universe sits so precisely at that balance is one of the great puzzles of cosmology, and the CMB provides the clearest evidence of it. What's striking about all this is how quiet it is. The most ancient and important light in the universe doesn't blaze or flash. It whispers. Its energy is low, its temperature barely above absolute zero. It doesn't change or flicker, and yet it contains everything. It's a kind of universal background note, a faint hum underlying all existence. Every star, every galaxy, every living thing exists against that backdrop. The CMB is the canvas upon which the universe has painted everything else. When you look up at the night sky, you're seeing light from stars that may be thousands or millions of years old. When astronomers use powerful telescopes, they can see galaxies billions of light years away, catching light that left them before Earth even formed. But when we detect the cosmic microwave background, we're looking back as far as it's physically possible to see. That light began its journey when the universe was less than 400,000 years old. Everything before that is beyond visibility. The CMB is not just old, it's the horizon of knowable history. The photons that left that first transparent universe are still on their way, travelling endlessly through expanding space. Some of them will reach us tomorrow, some in 1,000,000 years, though most already have. Every point in space continues to send and receive that ancient light, each region forever wrapped in its own version of the same story. And as time passes, as the universe grows colder and more diffuse, that story keeps unfolding, carried by the oldest light in the sky. The discovery of this light changed everything about how we understand the cosmos. It showed that the universe has a measurable history, that it began in a hot, dense state, and that it has been expanding and cooling ever since. It turned cosmology from speculation into observation. And it did so with extraordinary gentleness, not through bright explosions or dramatic evidence, but through a soft, even glow that fills the sky. If you could close your eyes and imagine the universe not as darkness dotted with stars, but as a single field of faint warmth, you'd be seeing it as it truly is. Everything else, all the bright objects, all the colours, all the forms, are small details drawn upon that ancient foundation. The CMB isn't just the oldest light. It's the background to everything that has ever existed. The quiet pulse that has been shining since the moment clarity first arrived. And as that light continues its journey, it carries within it more than temperature or structure. It carries potential. The trace of the universe's first fluctuations, the delicate variations that will one day become vast galaxies and the stars within them. Those seeds are still there, written in the faint pattern of microwaves that fills space. Every ripple in that pattern is a promise of what came next. The faint hum of the universe lingered, steady and constant long after the fog had lifted. The oldest light kept travelling outward, carrying its delicate variations like fingerprints impressed on a sheet of glowing silk. To the human eye, it would be invisible now, stretched and cooled by billions of years of expansion. But to the instruments built to detect it, that light carries a map, a record of the earlier structure, the first unevenness in an otherwise smooth cosmos. It's a map not drawn in ink or colour but in temperature and radiation. When scientists began to measure it precisely, they discovered that the universe itself was painted in static. That word, static, makes it sound random, like the hiss between radio stations or the fuzzy snow on an old television screen. In a way, that's not far off. The cosmic microwave background is indeed a kind of cosmic static. It's everywhere, unending, faint and even. But it's not meaningless noise, it's structured. The static has texture, patterns, and correlations that reveal the blueprint of everything that came after. Every patch of that background, every subtle change in brightness, represents a tiny variation in the density and temperature of the early universe. Those minute differences, frozen into the fabric of space when the first light escaped, became the seeds of galaxies, stars, and clusters. It's strange to think that the same phenomenon that once appeared as a nuisance in a radio telescope would turn out to be the universe's most valuable photograph. When Arno Penzias and Robert Wilson first heard the persistent hiss in their antenna, they couldn't have known that it was the sound of the cosmos speaking in microwaves. They thought it was interference. They thought it was pigeons. They didn't yet have the context to realise that they had stumbled upon the faint afterglow of creation. It was only after comparing their results with the theoretical predictions of physicists at Princeton, Robert Dicke, Jim Peebles, and their colleagues, that the truth became clear. The noise was not coming from Earth, nor from the galaxy. It came from everywhere, equally. It was cosmic. The realization changed everything. The Big Bang Theory, until then, had been one of several competing ideas about the origin of the universe. There were scientists who favoured the steady-state model, which proposed that the universe had always existed and always would, with new matter continuously created as it expanded. The discovery of the cosmic microwave background ended that debate. There was no steady state. The universe had a beginning, and the light from that beginning was still here. But at first, the detection was crude. Penzias and Wilson's antenna could only measure the average intensity of the radiation, not its details. It told us that the background existed, but not how it varied across the sky. To understand what those variations could reveal, scientists needed instruments designed specifically for that purpose. Over the next few decades, technology advanced enough to build them. In 1989, NASA launched the Cosmic Background Explorer, or COBE. Its mission was simple: to measure the spectrum and anisotropy of the cosmic microwave background with unprecedented precision. When the data came back, it showed two remarkable things. First, the CMB had an almost perfect black-body spectrum, meaning it was the cooled remnant of a once-hot thermal radiation field, exactly as predicted by the Big Bang Theory. Second, and even more importantly, it wasn't perfectly smooth. COBE detected tiny temperature fluctuations, just a few parts in 100,000, scattered across the sky. Those ripples were the first direct evidence of the universe's early structure. George Smoot, the project's principal investigator, famously said that it was like seeing the face of God. What he meant was that the pattern they had revealed was not random. It was the original blueprint for everything in existence. Those patterns of static were faint but meaningful. They showed that the early universe wasn't perfectly uniform after all. It had texture, patches that were ever so slightly warmer or cooler than others. In the warmer regions, the density was higher. In the cooler regions, lower. Gravity, over time, would magnify those differences. The denser regions would attract more matter, collapsing into the first galaxies and clusters, while the emptier regions would become the vast cosmic voids. In those first images of the microwave background, scientists were effectively seeing the universe as an infant, its future already written into the unevenness of its earliest light. After COBE came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. Its resolution was vastly superior. Where COBE could only see variations on large scales, WMAP could map the temperature differences across much smaller regions of the sky. With that data, cosmologists refined their understanding of the universe's age, composition, and geometry. The results were astonishingly consistent. The universe was about 13.8 billion years old, composed mostly of dark energy and dark matter, and geometrically flat. The static had become a map, and the map had become a measurement. The next leap came with the Planck satellite, launched by the European Space Agency in 2009. Planck produced the most detailed image of the cosmic microwave background ever made, with sensitivity fine enough to detect temperature differences of just a few microkelvins. Its data gave us the most accurate cosmological parameters to date, confirming, refining, and expanding everything we thought we knew. The Planck map revealed not only the temperature anisotropies, but also the polarization of the light, providing deeper clues about the processes that occurred in the early universe. When you look at that map, what you're seeing is the ultimate static, a speckled pattern of warm and cool spots, each representing a slightly different temperature from 13.8 billion years ago. The warm regions correspond to areas where the photons came from slightly denser parts of the early universe, the cool ones from less dense regions. The entire pattern is random in appearance but statistically precise, matching the predictions of quantum fluctuations stretched to cosmic scales by inflation. Every tiny spot on that map is a whisper of the quantum world, frozen into the sky. It's easy to forget that behind the mathematics and the measurements, this is a story of light. Light that has been travelling since the dawn of time. Each photon in the CMB has crossed billions of light years, dodging galaxies and clusters, redshifting all the while. Most of them have never interacted with anything since they were first released. They're pristine. When they strike our detectors, they bring with them the unaltered story of the early universe. The static that once frustrated radio engineers is, in truth, the most reliable signal nature has ever provided. The name microwave background can sound technical, but it's fitting. The radiation's wavelength lies in the microwave region of the electromagnetic spectrum, just between infrared light and radio waves. It's a frequency we can detect with antennas, but not with our eyes, and yet it's everywhere. The energy density of the CMB is about 400 photons per cubic centimetre, which means that in every room, in every cubic centimetre of space, hundreds of ancient photons from the Big Bang are passing through every second. The whole universe, including the air you breathe, is filled with this invisible light. To visualize it, you might imagine the faint static pattern of an old television screen, where no channel is tuned in. That chaotic fuzz of brightness and darkness isn't far from what the universe itself would look like in microwaves if you could see at those frequencies. It's not uniform grey, it's subtly varied, with patterns that encode vast information. The difference is that cosmic static isn't meaningless. It's a code that scientists have spent decades learning to read. When we interpret the CMB, what we're really doing is listening to the memory of the universe. The variations in the static correspond to acoustic oscillations, sound waves that rippled through the early plasma before light could move freely. Those sound waves left imprints on the density of matter, and when the light was finally released, those imprints were captured in its pattern. In other words, the CMB is a fossilized record of the universe's first vibrations. When scientists analyse it, they're hearing the echoes of sound waves that passed through the cosmos when it was only 380,000 years old. This connection between sound and static is more than poetic, it's physical. The early universe was dense enough for pressure waves to move through it like sound through air. Regions of higher pressure compressed and heated the plasma, while regions of lower pressure expanded and cooled it. These oscillations froze when the universe became transparent, leaving behind alternating bands of slightly different temperature and density. Those bands are what we see in the CMB's static pattern. The peaks and troughs of the cosmic sound waves have become the bright and dark spots on the map of the sky. Each scale of fluctuation tells us something specific, Large-scale variations correspond to regions that had time to oscillate only once before recombination. Smaller-scale variations show regions that oscillated multiple times. By analysing the relative strength of these variations, what scientists call the power spectrum, we can infer the universe's fundamental parameters. The precise positions of the peaks in that spectrum tell us the density of matter, the rate of expansion, and the nature of dark energy. All that information is encoded in what looks at first glance like noise. It's a remarkable thought, that by studying a pattern of static we can measure the age, shape, and content of the universe. And yet, that's exactly what we've done. The CMB has become the foundation of modern cosmology. It's the starting point for every model and the benchmark against which every theory must be tested. Without it, our understanding of the universe would be speculative. With it, we can describe cosmic history in precise numbers. Even the imperfections in the data tell a story. Tiny asymmetries in the static reveal hints of phenomena we still don't fully understand. The possibility of early gravitational waves, the fingerprints of inflation, or perhaps features imprinted by physics beyond our current theories. The CMB isn't just a record of what we know, it's a guide to what we don't. The notion of the universe being painted in static also carries a kind of quiet irony. When we imagine the cosmos, we picture it as majestic and orderly. Galaxies spiralling, stars burning, light streaming. But its earliest image, the first true photograph of everything, looks like noise, a field of uneven speckles, random to the eye but deeply ordered beneath the surface. The universe began not with form but with pattern. The beauty lies not in its neatness, but in its precision. The more we study this static, the more we realise that it connects everything. The galaxies we see today, billions of light years apart, share a common ancestry in those tiny ripples. The positions of stars, the formation of planets, even the eventual emergence of life, all of it can be traced back to the fluctuations frozen in the CMB. Every structure that exists, every atom that clumped together to form something larger, follows a path that began as a small deviation in that ancient noise. If you were to condense the entire history of the universe into a single image, it would be that map of cosmic static. The pattern contains everything. The seeds of matter, the rhythm of the early plasma, the curvature of space, the imprint of quantum fluctuations. It's the universe's first memory, captured in radiation instead of words. And as strange as it seems, we're still surrounded by it. Every moment the oldest light washes through space, indifferent to the passage of time, unchanged by the evolution of stars or galaxies. When it passes through us, it doesn't react or slow down. It keeps going, as it always has. The static hums quietly in the background, the universe's faintest song waiting for those who know how to listen. The discovery of this background radiation was, in a way, humanity's first direct connection to the beginning. It showed that the story of the cosmos isn't hidden in distant places, but present everywhere. Every point in space contains the same evidence, the same static, the same ancient light. The universe doesn't keep its history secret, it radiates it constantly. The static, when seen for what it truly is, isn't a blur of interference, it's the most meaningful noise in existence, a perfect pattern of imperfection, frozen in time, whispering the shape of everything that would follow. And as that faint pattern continued to stretch and cool, the universe that produced it began to evolve. Gravity was taking hold, dark matter was drawing structure out of chaos, and the quiet afterglow of creation was becoming the backdrop for new light. The static would remain forever, but within its stillness something dynamic was beginning. The slow and patient growth of form within the vast calm of the cosmic night. The light that filled the universe in its earliest days didn't just drift endlessly into emptiness. It carried information, precise, detailed, and ancient. When we look at the cosmic microwave background today, We aren't just seeing leftover radiation. We're looking at a map, a complete record of how the universe looked when it was less than 400,000 years old. Every point in that faint glow holds data about density, temperature, motion, and geometry. The map is written not in lines or symbols, but in variations of brightness, tiny differences so subtle they could easily be mistaken for noise. Yet together, they form the most comprehensive portrait of the cosmos ever made. It's a map of everything. When scientists first realised what the CMB represented, they understood that decoding it would be like reading the DNA of the universe. The radiation itself is uniform to 1 part in 100,000, but those minuscule fluctuations are crucial. They show where the universe was slightly denser and where it was slightly emptier, where sound waves rippled through the plasma and where gravity was beginning to take hold. They're the fossilised fingerprints of creation, preserved in light that has been travelling for nearly 14 billion years. Creating a map from that light isn't simple. The radiation comes from every direction, faint and constant. To record it, scientists build instruments that can measure temperature variations of just a few millionths of a degree. The data must be collected from above Earth's atmosphere, because even the faintest moisture or heat from the planet can distort the signal. That's why the great cosmic background missions, COBE, DOMAP and Planck, were all sent into space. From their vantage points beyond the atmosphere, they could listen to the sky with unmatched precision, tuning into a frequency that no human sense could ever perceive. The process begins with antennas that scan the sky, pixel by pixel, over months and years. Each measurement records how much radiation arrives from that part of the sky, and how its intensity compares to other regions. Once the full sky has been mapped, scientists can transform those raw measurements into a colour-coded image. The warm tones, often shown in red or orange, represent slightly hotter regions, where the early universe was denser. The cool tones, shown in blue, represent slightly cooler regions where it was less dense. These differences are tiny, often no more than a few hundred microkelvins apart, but together they form a precise picture of the early cosmos. At first glance, the resulting map looks like static, a mottled, uneven sphere of coloured speckles. But beneath that randomness lies order. The pattern of fluctuations isn't arbitrary. It follows exact statistical rules predicted by physics. The way those spots are distributed, their average sizes, their correlations across different scales, all of it reflects the physical processes that governed the early universe. The light from recombination carries the imprint of sound waves that rippled through the plasma, the influence of gravity pulling on matter, and even the subtle effects of dark matter shaping how those ripples evolved. The CMB map is not just a snapshot. It's a record of motion, a fossilised rhythm of the universe's first heartbeat. When the first maps were released, they were met with awe. The image produced by COBE in 1992 was coarse by modern standards, but it showed, for the first time, that the early universe had structure. That discovery transformed cosmology from theory to precision science. Suddenly, the Big Bang was not just a model, but a measured event. The variations COBE saw matched exactly what inflationary theory had predicted. Tiny, nearly scale-invariant fluctuations produced by quantum processes in the earliest fractions of a second. Those fluctuations, amplified by cosmic expansion, were the seeds of everything that would later exist. WMAP refined that map with greater resolution. Its data revealed multiple peaks in the power spectrum, patterns corresponding to different scales of oscillation in the early plasma. Each peak carried meaning. The first showed how matter and radiation interacted through sound waves. The second revealed the balance between baryonic matter and dark matter. The third and fourth peaks hinted at the curvature of space itself. By analysing the positions and amplitudes of those peaks, cosmologists could extract the universe's most fundamental parameters: its age, its expansion rate, its composition, and its geometry. The map was no longer just a picture. It was a set of equations made visible. Planck, the next generation of mission, brought the universe into even sharper focus. Its detectors could sense variations as small as 5/millionths of a degree across 9 frequency bands. That precision allowed scientists to separate the true cosmic signal from the foreground noise produced by our own galaxy. Dust and charged particles in the Milky Way emit their own microwaves, but Planck's multi-frequency design could distinguish those local emissions from the ancient background radiation. Once the galactic contamination was removed, the full cosmic pattern emerged, a pure, detailed map of the sky, as it was when light first escaped. That map, released in 2013, became a cornerstone of modern cosmology. It confirmed that the universe is 13.8 billion years old, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It showed that space is flat to within 1/10 of 1%. It also revealed the seeds of large-scale structures, the same filaments and clusters that define the cosmic web today. In the mottled speckles of microwaves, scientists could see the outlines of the universe's entire future. One of the most profound aspects of the CMB map is that it gives us a view not just of the past, but of the laws that shaped it. The statistical distribution of its fluctuations follows what's known as a Gaussian pattern, meaning that the variations are random but follow a predictable probability curve. This pattern is what inflation theory predicts for quantum fluctuations stretched to cosmic scales. That agreement between theory and observation is one of the strongest pieces of evidence we have that inflation actually occurred. The map of everything is also a map of how physics behaved when space itself was born. To extract information from this map, cosmologists perform a kind of cosmic archaeology. They decompose the temperature fluctuations into spherical harmonics, mathematical functions that describe how different angular scales contribute to the overall pattern. Large-scale variations correspond to low multipoles, small-scale ones correspond to higher multipoles. By analysing the power at each scale, scientists can reconstruct the history of density fluctuations, the composition of the universe, and even the possible presence of gravitational waves. It's a translation from colour to code, from static to structure. Every feature of the CMB tells a story. The smallest variations reveal how baryons, the normal matter that makes up atoms, interacted with photons in the early plasma. The slightly larger scales show how dark matter influenced those interactions by adding gravitational weight without contributing radiation pressure. The larger scales carry the imprint of the universe's overall shape and topology. Even tiny asymmetries or irregularities could point to phenomena beyond our current understanding, perhaps traces of other universes or subtle effects of primordial gravitational waves. The map is simple to look at but almost limitless in what it contains. Even polarization, the orientation of the light waves, adds another layer of meaning. As the photons scattered off electrons during recombination, they became slightly polarized, their electric fields aligned in specific directions. Measuring that polarization allows scientists to separate the CMB's signal into 2 components: E modes, which arise from density variations, and B modes, which could be caused by gravitational waves from inflation. Detecting those B modes would be like hearing the faint tremor of space-time itself from the first instant of creation. While their existence remains uncertain, ongoing experiments continue to search the sky for that subtle pattern within the map. What's striking about the CMB map is how balanced it is. There's no preferred direction, no centre, no edge. The fluctuations look statistically the same everywhere. This isotropy confirms that the universe, on the larger scales, is homogeneous, that the same physical laws apply in all directions. It's a principle known as the cosmological principle, and the CMB provides its most convincing evidence. The map shows that the universe doesn't just appear uniform, it actually is, down to astonishing precision. There's something almost philosophical about that. The sky we see, with all its unevenness, the stars, the Milky Way, the constellations, is just a thin layer of nearby structure. Behind it lies the true background, the foundation of everything, perfectly even and calm, with only the smallest ripples. The CMB map reminds us that beneath the complexity of galaxies and clusters, the universe began in simplicity. All the variety we see today is built on a background of near perfection, disturbed only by tiny quantum fluctuations that inflation stretched into cosmic scales. When cosmologists look at that map, they don't just see colour gradients or data points. They see the story of structure, how tiny variations in density grew into the vast architecture of the cosmos. The warm regions on the map became galaxies. The cool regions became the empty spaces between them. In this way, the CMB isn't just a relic of the past. It's a photograph of the universe's potential, captured before it unfolded. Even now, scientists continue to refine the map, to remove noise, to cross-check observations, to compare different data sets. Every improvement brings new precision, and occasionally new puzzles. One of those puzzles is the so-called cold spot, a region of the CMB that appears slightly cooler and larger than statistical models predict. Some suggest it might be caused by a vast underdensity of matter, a cosmic void along our line of sight. Others wonder if it could be evidence of something deeper, perhaps a signature of new physics or even an interaction with another universe beyond our own. No one knows yet. The map continues to hold mysteries, as any good map should. The power of this map lies not only in its data, but in its universality. It's the one sky every observer in the universe would share. No matter where you stand, if you could detect microwaves, you'd see the same pattern surrounding you. The details might shift slightly because of motion or local structure, but the overall pattern, the fingerprint of the early cosmos, would be the same. The map doesn't belong to Earth or to humanity. It belongs to space itself. When you look at a projection of the CMB, it's often shown as an oval, stretched to display the entire celestial sphere on a flat surface. The colours vary from deep blue to bright red, representing temperature differences so small they defy normal comprehension. The pattern looks random, almost abstract, but it's the most precise representation of reality we've ever made. In that randomness lies all order, all structure, all time. It's humbling to realise that everything, from the spiral arms of galaxies to the chemical composition of stars to the life on this planet, can be traced back to a pattern of temperature differences smaller than 1/10,000th of a degree. The CMB map is the origin of complexity, the quiet blueprint from which the universe constructed itself. Each variation in that ancient radiation represents the faint memory of a vibration, a pressure wave, a quantum fluctuation. Those whispers of density and temperature became the pillars of galaxies, the frameworks of clusters, and the filaments of the cosmic web. The beauty of the map isn't in its colours or shapes, but in its meaning. It's a record of balance, between expansion and gravity, between radiation and matter, between chaos and structure. It's the point where simplicity tipped into diversity, where the uniform glow of the early universe began to fold into the intricate forms we see now. And though the map looks frozen, it's still alive in its consequences. The patterns it records continue to shape the universe today. The same gravitational imbalances that once existed in that early plasma are still pulling galaxies toward one another. The same expansion that stretched those photons continues to stretch space now. The same dark energy that influenced the early universe still drives its acceleration. The map of everything isn't just a record of where we've been, it's a guide to where we're going. Even as we learn to read it more clearly, the map keeps reminding us of something profound. That the universe is knowable, that light, no matter how faint, carries the truth of its origins. That the pattern of static left over from the dawn contains enough information to describe everything that followed. And that within the quiet hum of ancient radiation lies the most complete story ever told, written not in words or images, but in the temperature of light itself. As that light continues its journey across expanding space, still cooling, still stretching, the map it carries becomes even more precious. Each photon that reaches us adds another data point, another pixel in the cosmic picture. And though the radiation grows fainter with time, its message remains clear. A record of how the universe once looked when it was new, before stars, before galaxies, before darkness was even dark. That map, the one drawn in static, still surrounds us. It isn't distant or hidden. It's here, passing through every space, every moment, every atom. The universe wrote its memory in light, and that light never stopped moving. Even now, as we drift within it, we remain part of that pattern, woven into the map of everything. The map of the early universe looks, at first glance, like noise, a field of faint mottled patches, warmer regions and cooler ones scattered across the sky with no obvious pattern. But within those tiny ripples lies everything. The entire structure of the cosmos, every star, every galaxy, every atom of the visible universe can trace its origin back to those fluctuations. The universe we see now, vast, luminous, and full of contrast, was once a nearly featureless sea. What made it come alive were the smallest imperfections imaginable. Tiny ripples. Those ripples were not random chaos. They were the natural consequence of the laws of physics acting in the earliest moments of time. Even when the universe was still opaque, filled with the hot plasma of protons, electrons, and photons, it wasn't perfectly smooth. Small variations in density and temperature existed everywhere. They were born from quantum fluctuations, the inevitable jitter of energy that occurs at the smaller scales. In the first fractions of a second after the Big Bang, when the universe was smaller than an atom, those fluctuations were microscopic. But as space expanded, especially during the brief explosive phase of cosmic inflation, those tiny disturbances were stretched to cosmic proportions. What had once been quantum scale became astronomical. By the time the universe cooled enough for light to move freely, those small variations had become measurable differences in density. Some regions were just a little denser, some a little less. The difference was minuscule, about 1 part in 100,000. Yet that was enough. Gravity, always patient, amplified those variations over billions of years. The slightly denser regions pulled in more matter, and the process built upon itself. Over immense spans of time, those tiny ripples in the early plasma became galaxies, clusters, and the vast cosmic web that defines the structure of everything. When scientists study the cosmic microwave background, those ripples are what they're really looking for. The CMB is almost uniform, but its subtle temperature variations, the warm and cool patches seen in maps from Planck and WMAP, hold the record of those early density differences. The hotter regions correspond to slightly denser zones in the young universe, where gravity was already tugging harder. The cooler regions correspond to less dense zones, where expansion was winning the battle. Each fluctuation is a seed, and together they form the blueprint for all future structure. It's difficult to grasp just how delicate those imbalances were. If the universe had been perfectly smooth, nothing would ever have formed. Gravity would have had no foothold. Matter would have remained evenly distributed forever, a thin gas expanding into infinite nothing. But if the variations had been too large, the universe would have collapsed in on itself before stars or galaxies could form. The balance had to be almost perfect, irregular enough to allow structure, but smooth enough to remain stable. The fact that the fluctuations fall within exactly that narrow range is one of the most remarkable coincidences in nature. It's as though the universe tuned itself to the threshold between chaos and emptiness. In the early plasma, those ripples weren't just static differences. They moved. They oscillated like sound waves travelling through air, compressing and rarefying as radiation pressure and gravity pulled against each other. These acoustic oscillations left their fingerprints on the CMB. When the universe became transparent, those oscillations froze in place, and the pattern of the ripples was preserved in the light. We can still see that frozen sound in the temperature variations across the sky. It's a fossil of motion, a memory of how the early universe vibrated before it became transparent. Each ripple tells us something specific about how the universe behaved at that time. The amplitude of the fluctuations shows how strong gravity was compared to radiation pressure. The size of the ripples indicates how long sound could travel through the plasma before light decoupled. Even the shape of the pattern reveals the curvature of space and the amount of dark matter present. It's astonishing how much information can be drawn from such subtle differences. From variations measured in microkelvins, we can reconstruct billions of years of cosmic evolution. The most precise measurements of these ripples come from satellites like Planck, which mapped the entire sky in multiple frequencies to filter out foreground noise. When scientists analysed the data, they produced what's called a power spectrum, a graph showing how much fluctuation exists at different angular scales. The peaks in that graph correspond to the fundamental notes of the universe's early oscillations, the harmonics of its first vibrations. Those peaks match perfectly with the predictions of physics. Each one corresponds to a different balance between matter, radiation, and dark energy. It's as though the universe played a chord at its birth, and we can still hear its echo today in the pattern of the microwave background. The beauty of these ripples is that they bridge the smallest and largest scales of reality. They began as quantum fluctuations, tiny random variations in the vacuum energy of the early universe. Quantum mechanics tells us that energy can never be perfectly uniform at microscopic scales. Even in apparent emptiness, fields fluctuate. During inflation, those fluctuations were stretched far beyond their original size, turning subatomic uncertainty into cosmic structure. When we measure the CMB, we're seeing direct evidence of quantum mechanics imprinted on the sky. The universe's largest features were born from its smallest uncertainties. The ripples also reveal how finely balanced the universe's contents were in its infancy. About 75% of the energy density came from radiation, 25% from matter, and a trace from dark energy. The way those components interacted determined how the ripples evolved. In regions where matter was dominant, gravity caused compression. Where radiation dominated, pressure resisted that collapse. The interplay between the two created standing waves, regions of compression and rarefaction frozen into the CMB pattern. By analysing these, scientists can infer not just how the universe looked, but how it behaved moment by moment as it expanded and cooled. When you look at a CMB map, you're seeing a snapshot of the universe's texture just after it became transparent. The bright patches are places where matter and radiation were slightly denser, the dark patches where they were less so. The scale of those patterns, the average size of a fluctuation, corresponds to about 1 degree on the sky, which equals several 100,000 light-years at the time of recombination. From that scale, we can deduce the sound horizon, the maximum distance a sound wave could have travelled through the early plasma. That distance acts as a kind of standard ruler for cosmology. By comparing it to similar patterns seen in the distribution of galaxies today, we can measure how the universe has expanded over time. Those tiny ripples, then, are not just relics, they're tools. They let us calculate the rate of expansion, the age of the universe, and even the mysterious properties of dark energy that drive cosmic acceleration. The faint irregularities in the microwave background are the calibration marks of the cosmos, the baseline against which all other measurements are compared. Without them, we would have no cosmic scale. It's fascinating to realise that these ripples also set the stage for temperature itself. When the universe was perfectly uniform, there was no difference between one region and another. No gradients, no flows, no definition of heat in the way we experience it. The emergence of these small fluctuations gave the universe its first contrast, the first thermodynamic landscape. From them came not only structure, but the possibility of energy moving from one place to another, the first hint of dynamics. In that sense, the ripples didn't just shape matter, they defined time, movement, and change. When cosmologists refer to the CMB as the baby picture of the universe, they mean it literally. It's the earliest photograph we can take, showing the cosmos as it was in its infancy. But unlike a human photograph, which captures only the surface, this one captures the underlying process. Each pixel contains information about sound waves, gravity, and quantum effects all at once. The ripples we see are the universe's first expression of difference, the first contrast in a reality that had been almost perfectly even. From those contrasts, everything else followed. If you were to trace the evolution of one of those ripples forward through time, you'd see it grow and change. Over the next few million years after a combination, gravity would continue to pull matter toward the denser regions. Hydrogen gas would begin to accumulate, slowly forming the first clouds. As those clouds grew denser, their centres would heat, and eventually the first stars would ignite. The bright galaxies we see scattered across the modern sky all began as faint imprints in that early pattern. Every cluster of galaxies, every filament of the cosmic web, every spiral arm of every star system can trace its lineage back to one of those ripples. The connection between that ancient pattern and the modern universe is astonishingly direct. Computer simulations can start with the CMB data, the exact pattern of temperature and density variations measured by Planck, and evolve it forward using the known laws of physics. The resulting structures match what we observe through telescopes today. Galaxies form where the CMB showed slightly higher density. Voids appear where it showed less. The map of the early universe predicts the structure of the current one with extraordinary accuracy. It's one of the great triumphs of modern science, to be able to take a faint glow in the microwave spectrum and use it to reconstruct the entire visible cosmos. The ripples also reveal the incredible precision of the universe's laws. Every physical process that occurred during those early moments followed mathematical relationships we can still describe. The speed of sound in the plasma, the rate of expansion, the strength of gravity, all consistent, all measurable. When we compare our models to the actual CMB data, the match is almost perfect. That precision suggests that the same laws governing particles and energy in laboratories on Earth also governed the cosmos when it was less than 1 million years old. The smallest ripples confirm the deepest symmetry. Even so, there are mysteries within the data. Some regions of the CMB show slight asymmetries, a tiny excess of power on one side of the sky compared to the other. Some models predict this could be a statistical fluke, but others wonder if it hints at physics beyond the standard model. Perhaps traces of early anisotropy or evidence of cosmic structures larger than the observable universe. There's also the question of non-Gaussianity, the possibility that the fluctuations are not perfectly random, but carry subtle correlations that could reveal how inflation operated. The ripples contain clues we haven't yet learned to read. For all its technical depth, though, the essential truth remains simple. Without those ripples, nothing would exist. They're the imperfections that made perfection interesting, the differences that allowed gravity to sculpt matter into stars and galaxies. The entire history of structure formation, from the first hydrogen clouds to the vast web of galaxies spanning billions of light years, began with those tiny variations in the temperature of ancient light. It's humbling to think that the universe's immense diversity, the beauty of nebulae, the complexity of planetary systems, the emergence of life, all stems from fluctuations smaller than 1/10,000th of a degree. The same laws that produce those ripples are still at work today, continuing to shape galaxies, stars, and the space between them. The ripples are not a relic of the past, they are the foundation of the present. As the universe continued to expand and cool, those patterns remained imprinted in the radiation, but the matter within them began to evolve. The photons kept travelling, stretching into microwaves, forming the cosmic background that still surrounds us. The matter condensed, dark matter halos formed, and the stage was set for light to return, not as the uniform glow of the CMB, but as the first stars flickering into existence. The cosmic dawn was approaching, built entirely upon the faint ripples left behind. The meaning hidden within those tiny variations reaches beyond physics. It speaks to a principle that runs through everything, that small differences, amplified by time, can create immense complexity. The universe didn't begin with grand design or structure. It began with randomness shaped by law, magnified by gravity, and unfolded through time. From that randomness came everything that breathes, moves, and wonders. The ripples that once spread through the plasma of the young universe carried more than the seeds of structure. Hidden within them was the shape of space itself. When scientists look at the cosmic microwave background today, they're not just studying the faint variations in temperature, they're measuring the geometry of everything. It's one of the strangest realizations in cosmology, that by examining the light left over from the Big Bang, we can determine whether the universe is curved or flat, whether space itself bends inward or outward, and how infinite it might be. The map of ancient light becomes, in this way, a ruler for the universe's deepest architecture. Geometry in everyday life is simple. Straight lines, circles, angles and distances all obey familiar rules. Two parallel lines never meet. The sum of the angles in a triangle is always 180 degrees, but those rules only hold in flat space. On a curved surface, geometry behaves differently. On Earth's surface, for instance, two lines of longitude start parallel at the equator but meet at the poles. A triangle drawn on a sphere has more than 180 degrees. That same principle applies to the universe as a whole. Space can curve, and the way it curves affects everything. How light travels, how galaxies move, and even how the universe will evolve in the future. The idea that the universe has geometry may sound abstract, but it's central to Einstein's theory of general relativity. According to that theory, space and time form a single fabric, space-time, which is shaped by the presence of matter and energy. Mass bends space, and curved space tells mass how to move. The universe, in this sense, isn't expanding into something else. The expansion is the stretching of space itself. Its geometry determines the paths of light rays and the fate of expansion. If the universe has enough mass and energy, its gravity will cause it to curve inward, like the surface of a sphere. If it has too little, it will curve outward, like a saddle. If the balance is just right, space will be flat. Each of these shapes carries a different destiny. A positively curved universe, like a sphere, would eventually stop expanding and collapse in a big crunch. A negatively curved one would expand forever, its galaxies rushing apart into infinite coldness. A flat universe sits between these two extremes, expanding forever, but at a rate that gradually slows. Which shape reality takes depends on the universe's total density, how much matter, radiation, and dark energy it contains. The critical density, a specific value of mass energy per cubic meter, defines the dividing line between open, closed, and flat. For decades, scientists debated which description applied to our cosmos. Theories alone couldn't decide it. What was needed was a way to measure the geometry directly. That's where the cosmic microwave background came in. The CMB provides not only a record of temperature fluctuations, but also a set of standard lengths, patterns of known physical size imprinted at the time of recombination. The most important of these is the sound horizon, the maximum distance that a sound wave could have travelled through the early plasma before light decoupled. That distance is known precisely from physics. By observing how large that feature appears on the sky today, we can infer the curvature of space. If space is flat, the sound horizon will subtend an angle of about 1 degree on the sky. If space is positively curved, it will appear larger because light paths converge. If space is negatively curved, it will appear smaller because light paths diverge. Measuring that angle with high precision tells us whether the universe bends, and if so, how much. The first satellite to attempt this measurement was WMAP, which mapped the entire sky in microwaves for nearly a decade. When scientists analysed its data, they found that the characteristic scale of the temperature fluctuations matched the prediction for a flat universe almost perfectly. Planck, with even greater precision, later confirmed it. The geometry of the universe, on the largest observable scales, is flat to within a fraction of 1%. Parallel lines, stretched across billions of light years, remain parallel. Triangles drawn with cosmic edges still add up to 180 degrees. Flatness doesn't necessarily mean infinity, but it strongly hints at it. In a perfectly flat universe, space extends without curvature or boundary. It could, in principle, go on forever. Yet because we can only observe so far, limited by the finite age of light, we can never know for sure whether the universe is truly infinite or merely very large. The observable universe, the region from which light has had time to reach us since the Big Bang, is about 93 billion light-years across. Beyond that horizon, the universe may continue endlessly or curve back on itself in ways we can't detect. The CMB gives us the geometry of what we can see, but not the full extent of what exists. The question of the universe's shape has fascinated cosmologists for generations because it connects something profoundly abstract, the curvature of space, with something measurable. The pattern of hot and cold patches in the CMB isn't just random data, it's a projection of the universe's three-dimensional geometry onto a two-dimensional sphere. By analysing those patterns statistically, scientists can test whether the rules of Euclidean geometry apply across cosmic distances. So far they do. The universe, as far as we can tell, is remarkably flat. That flatness poses its own mystery, though. In the early universe, any slight deviation from perfect flatness would have grown rapidly over time. If space were even slightly curved at the beginning, that curvature should dominate today. The fact that it doesn't suggest that something smoothed it out, some process that drove the universe toward flatness long before the CMB formed. That process is what we call inflation. During inflation, space expanded exponentially, ironing out any initial curvature like a taut sheet. The CMB's observed flatness is one of the strongest pieces of evidence that inflation actually occurred. When we talk about the geometry of space, it's easy to forget how deeply it shapes what we see. The very concept of distance depends on curvature. In a flat universe, light travels in straight lines, and parallel beams remain parallel. In a curved one, light bends. Distant objects appear larger or smaller than they would in flat space. Time itself is influenced too. The expansion rate governed by the geometry affects how fast clocks would tick in different epochs of cosmic history. Everything, from the apparent brightness of supernova to the separation of galaxies, carries the mark of the universe's shape. The CMB acts as a kind of cosmic ruler that allows us to calibrate those distances. The patterns we see in its fluctuations form a baseline that all later observations must match. When we measure galaxies, quasars, or gravitational lensing, we can compare those results to the CMB-derived geometry to check for consistency. So far, everything aligns. The same flat geometry explains all observations. That unity gives cosmology a coherence that's rare in science. A single model that connects the smallest quantum fluctuations to the largest structures imaginable. But flatness doesn't necessarily mean featureless. The universe can be flat and still have complex topology. Just as a sheet of paper can be rolled into a cylinder without changing its local geometry, space itself could wrap around in ways we haven't yet detected. If the universe were finite but unbounded, like a higher dimensional analogue of a torus, light could travel all the way around it, eventually returning from the opposite direction. In that case, the CMB might contain repeating patterns, identical spots in different parts of the sky where light has circled the cosmos. Scientists have searched for such patterns, but so far none have been found. If they exist, the universe must be vast enough that light hasn't yet had time to complete a full circuit. Even the tiny variations in the CMB can tell us about geometry in subtle ways. The way the polarization of light aligns across the sky reveals how space curves along our line of sight. Slight distortions in the CMB caused by gravitational lensing, where massive structures bend the path of photons, also allow cosmologists to reconstruct the distribution of matter and the shape of the gravitational field. These effects provide another test of geometry, one that connects the ancient universe to the modern one. The ripples we see in the CMB are not static. As they travel through the evolving universe, they're deflected and stretched by the large-scale structure that formed later. By studying those distortions, scientists can map the geometry not just of the early cosmos, but of the entire history between then and now. The remarkable thing about this cosmic geometry is how consistent it is. From the Planck era to the present, the same physical principles describe how space bends, how energy moves, and how light travels. The same equations that describe the bending of starlight by the sun also describe the curvature of the entire universe. It's all one continuum, from the smallest scales to the largest. When you think about it, the idea of a flat, possibly infinite universe is both simple and unsettling. It means there is no edge, no centre, no boundary to cross. The observable universe, the part we can measure, is only a tiny portion of an unfathomably larger whole. Beyond the horizon of the CMB there are regions we can never reach, not because they're hidden by matter, but because light itself hasn't had time to travel that far. The geometry of infinity isn't about distance, it's about limitation, the recognition that the horizon of visibility defines our entire sense of reality. Even so, we can infer what lies beyond. The uniformity of the CMB, the consistency of its patterns, tells us that the same laws apply everywhere. If we could step outside our cosmic horizon and look back, we'd see another sphere of ancient light, nearly identical to ours. Every observer in the universe, no matter where they are, is surrounded by their own CMB. Each one sees the same geometry, the same pattern of ripples, the same faint afterglow. The cosmos looks the same from every vantage point because space itself is homogeneous and isotropic on large scales. It's not just vast, it's consistent. The geometry revealed by the CMB also connects deeply with time. As the universe expands, the curvature doesn't remain fixed. It evolves with the density of matter and the influence of dark energy. In the earliest moments, when radiation dominated, the geometry was nearly flat but slightly dynamic. As matter took over, gravity began to bend space more strongly. Now, as dark energy accelerates expansion, the curvature is slowly relaxing again toward flatness. The shape of the universe isn't static. It's a living aspect of its history, written into every stage of its evolution. When scientists model that evolution, they can use the CMB as the starting point. By taking the observed geometry and running it forward in time, they can predict how galaxies should distribute, how clusters should form, and how the cosmic web should stretch. When they compare those predictions to actual surveys of galaxies, the match is astonishing. The same geometry that shaped the CMB's ripples still governs the structure of everything we see. The curvature of space is the invisible framework upon which the universe has built itself. If you think of the CMB as a photograph of the universe's first light, then its geometry is the camera lens, the thing that determines how that light is projected and how we interpret its scale. The patterns of temperature fluctuations act like celestial landmarks. By measuring their apparent size and spacing, cosmologists can reconstruct the underlying shape of space. Every pixel in the map becomes a coordinate in an invisible, multi-dimensional geometry. For all its precision, this knowledge still leads to wonder. The idea of a flat or infinite universe challenges intuition. We're used to edges, to boundaries, to beginnings and endings. Infinity resists that. It offers no horizon except the one defined by light's finite speed. The CMB marks that horizon, the farthest we can see, and yet beyond it, the geometry may continue forever. Every photon we detect comes from that boundary, telling us that the universe, while vast, is also self-consistent. It's the same everywhere we can look, and perhaps everywhere we cannot. The geometry of infinity is, in the end, both scientific and philosophical. It reminds us that our measurements, no matter how precise, are bound by the limits of perception. The universe may be infinite, but our access to it is finite. The CMB is our window, our horizon of knowledge. Beyond it lies a continuation of the same fabric, expanding, cooling, and perhaps carrying patterns we'll never see. Yet even within that limitation, there's completeness. The data we have is enough to describe the whole with astonishing accuracy. The geometry may be infinite, but understanding it begins with a finite patch of sky. As the ancient light continues to drift across expanding space, it still follows the same straight paths defined by flat geometry. Those paths stretch endlessly, uncurved and unbroken, carrying photons that began their journey when the universe was young. Every one of them traces a segment of infinity, a line drawn through space-time from the beginning to now. Together, they fill the universe with a quiet order, the geometry of light in motion, the structure of expansion itself. Before the universe became transparent, before the light we now call the cosmic microwave background began its long journey, there was another moment, one far earlier, far shorter, and far more dramatic than anything that would follow. It lasted less than a fraction of a second, yet it shaped everything that came after. That moment is known as inflation, and its traces are still visible in the sky today. The faint ripples we see in the CMB, the remarkable flatness of space, and the uniformity of temperature across the cosmos all carry the signature of that brief, extraordinary expansion. The echoes of inflation are woven into the oldest light we can see. To understand inflation, it helps to remember what the Big Bang theory describes. Not an explosion in space, but an expansion of space itself. In the first instant after the Big Bang, the universe was unimaginably hot and dense, filled with energy distributed almost perfectly evenly. But even a universe that expands smoothly faces problems. One of them is the horizon problem. Opposite sides of the sky have nearly identical temperatures, yet they are so far apart that light could never have travelled between them to even things out. Another is the flatness problem. The universe today appears almost perfectly flat, meaning that its total energy density was balanced with incredible precision in the beginning. Without something to explain that balance, it would seem like an impossible coincidence. Inflation resolves both issues elegantly. According to the theory, the universe underwent a brief period of exponential expansion during its earliest instant, roughly between 1036 and 1032 seconds after the Big Bang. In that unimaginably small sliver of time, space grew by a factor of at least 1026 in size. Distances smaller than a proton were stretched to scales larger than entire galaxies. This rapid expansion would have smoothed out any irregularities, flattened the overall curvature, and stretched quantum fluctuations to cosmic proportions. What had once been microscopic became astronomical. Inflation wasn't an explosion of matter outward into empty space. It was the stretching of space itself. Every point in the universe expanded away from every other point. The distances between particles increased faster than light could travel, not because anything moved through space faster than light, but because space itself expanded. This distinction is important. The speed limit imposed by relativity applies to motion within space, not to the expansion of space itself. Inflation doesn't break the rules, it defines them on a larger scale. When inflation ended, the energy driving it converted into a burst of particles and radiation, the event we commonly call the Big Bang. That transition filled the universe with the hot plasma that would eventually cool into atoms, stars, and galaxies. In a sense, inflation was the prelude, the silent overture that set the stage for everything that followed. It created the uniform canvas on which the later evolution of the universe could unfold. The evidence for inflation comes from its imprints on the cosmic microwave background. The tiny fluctuations in temperature and polarization that we see in the CMB match exactly what inflation predicts. The variations are nearly scale invariant, meaning that their strength is roughly the same across a wide range of sizes, and they follow a Gaussian distribution, as expected from quantum fluctuations stretched to cosmic scales. The flatness of the universe, the uniformity of temperature, and the slight anisotropies in the CMB are all natural consequences of inflation. The process itself is thought to have been driven by a field, a form of energy that filled all of space. Cosmologists call it the inflaton field, though its exact nature remains unknown. During inflation, this field was trapped in a high-energy state, causing space to expand exponentially. When it decayed into a lower energy state, that energy was released as radiation and matter, reheating the universe and marking the beginning of the standard Big Bang evolution. The shape of the inflaton's potential energy curve, how it changed as the field decayed, determines the details of inflation and its observable consequences. Different models predict slightly different patterns in the CMB, and scientists use these predictions to test which version fits the data best. One of the most compelling pieces of evidence comes from the pattern of polarization in the CMB. When photons last scattered off electrons during recombination, they became polarized in a way that depends on the density and motion of the plasma, and also on the presence of gravitational waves. Inflation predicts that gravitational waves, ripples in space-time itself, would have been generated during the rapid expansion. These waves would leave a unique signature in the CMB's polarization, known as B modes. Detecting them would provide direct confirmation that inflation occurred. So far, the search for primordial B modes continues. In 2014, a team using the BICEP 2 telescope at the South Pole announced what appeared to be a detection, but later analysis showed that most of the signal came from galactic dust. Since then, experiments such as the South Pole Telescope, the Atacama Cosmology Telescope, and the upcoming Lightbird mission have refined the search. The goal is to distinguish the faint curl pattern of inflationary gravitational waves from other sources of polarization. Even without a confirmed detection, the upper limits measured so far are consistent with inflationary theory. The echoes are subtle, but they align with what the theory predicts. Inflation also explains the origin of the cosmic ripples themselves. Quantum mechanics tells us that even empty space is not truly empty. It seethes with fluctuations, tiny variations in energy that appear and disappear constantly. During inflation, space expanded so rapidly that these quantum fluctuations were frozen into place, stretched to macroscopic scales. Regions where the energy density was slightly higher became the seeds of later structure. In this way, the universe's largest structures were born from the smallest possible origins. The galaxies, stars, and planets that exist today owe their existence to quantum uncertainty magnified by cosmic expansion. It's remarkable how consistent the data is with this picture. The amplitude of the CMB fluctuations, their distribution, and their statistical properties all match what inflation predicts. The universe is not just uniform, but slightly imperfect, exactly as expected from quantum noise amplified across the cosmos. The balance between smoothness and structure, between emptiness and form, is the signature of inflation written across the sky. Even the overall flatness of space, the geometry we measured in the previous section, is a natural consequence of inflation. During exponential expansion, any initial curvature would have been stretched to near flatness, just as the surface of a balloon looks flatter the more it's inflated. If the universe had even a tiny amount of curvature before inflation, it would now be imperceptible. That prediction matches our observations perfectly. The universe we see is flat because inflation made it so. Yet inflation, for all its success, raises profound questions. What caused it to start and what caused it to stop? If it began with a field trapped in a high-energy state, what set that state in motion? What if inflation never stopped completely, but continued in other regions beyond our observable universe? Some versions of inflation theory suggest that our universe is just one bubble in a vast multiverse, a patch of space where inflation ended while continuing elsewhere. In that picture, space is eternally expanding, creating new regions where the process repeats. Each region could have different physical constants, different laws, even different dimensions. Our observable universe would then be just one local echo in an infinite cosmic symphony. Whether or not that's true, the evidence we can see remains the same. The CMB carries the imprint of an early, rapid expansion that set the universe on its current path. The echoes of inflation are visible in every direction, not as sound, but as structure, temperature and light. Each warm and cool patch in the microwave background is a frozen memory of that expansion, the result of quantum fluctuations stretched across the cosmos. Inflation also tells us something profound about the nature of time. During that brief moment, the universe didn't just grow, it reset. Any pre-existing irregularities were erased, any previous structures smoothed away. What we call the beginning may not have been the absolute start of everything, but rather the start of the universe as we can observe it. Inflation wiped the slate clean, giving rise to the conditions necessary for the Big Bang to unfold as it did. Before that, if there was a before, space and time themselves may have existed in a very different form. The CMB in this sense marks not the first moment, but the first visible moment, the point where history became measurable. The concept of inflation also bridges physics at every scale. It connects quantum mechanics, the theory of the very small, with cosmology, the science of the very large. The fluctuations that began as quantum events became the structure of galaxies. The energy of a microscopic field determined the geometry of the universe. The smoothness of space on cosmic scales reflects the randomness of particles smaller than atoms. In that connection lies one of the deepest insights of modern science, that the universe's vastness and its minuteness are two sides of the same coin. Every measurement of the CMB continues to refine our understanding of this process. The precise tilt of the power spectrum, a slight decrease in fluctuation amplitude at smaller scales, matches what inflationary models predict for a universe driven by a slowly rolling scalar field. The near-perfect Gaussian distribution of fluctuations shows that they originated from quantum processes rather than chaotic initial conditions. Even the small deviations from perfection hint at the physics of the inflaton field, how it decayed, how quickly inflation ended, and how the universe reheated afterward. Reheating itself was a remarkable event. When inflation ended, the potential energy of the inflaton field converted into a burst of particles, filling space with radiation and matter. Temperatures soared to unimaginable levels, perhaps as high as 1027 Kelvin. In that instant, the universe was reborn as a hot, dense plasma, beginning the phase we call the Big Bang. The smooth, empty expanse created by inflation became a cauldron of creation once again. That transformation from vacuum energy to particle energy is what set the universe on the path toward atoms, stars, and galaxies. The echoes of inflation didn't fade with that transition. They became the framework for everything that followed. The density variations created by quantum fluctuations continued to grow under gravity, eventually forming the structures we see today. The uniformity of temperature, the flatness of space, and the distribution of galaxies all trace their origins to that single, fleeting moment of exponential growth. The universe's entire character, its shape, scale, and evolution, was defined in less than a heartbeat. Even though we can't observe inflation directly, its effects are measurable everywhere. The CMB is its most visible residue, but there are others. The large-scale distribution of galaxies, the behavior of dark energy, and the overall isotropy of the cosmos all reflect its influence. Inflation set the initial conditions, and the universe has been unfolding according to those conditions ever since. What's striking about inflation is its simplicity. It requires only that space contain a form of energy that remains roughly constant as it expands. That's enough to drive exponential growth. Yet from that simple principle emerges a universe filled with complexity. A cosmos with billions of galaxies, each containing billions of stars, spread across billions of light years. The difference between the smooth energy of inflation and the structured universe we see today is time, governed by physics. In many ways, inflation was the first act of creation in the observable sense, not the beginning of existence itself, but the beginning of order. It took whatever chaos or randomness may have existed and stretched it into coherence. The result was a universe balanced on the edge of perfection, smooth enough to be stable, uneven enough to create. Those uneven patches, faint and ancient, are what we now detect as ripples in the CMB. They are the echoes of inflation, written into the oldest light in existence. When scientists look at the CMB, they are, in a sense, looking at the boundary between the visible universe and the unseeable inflationary past. The faint microwaves that reach us from that horizon are the first photons to travel freely through space, but their pattern was shaped by events that happened long before light existed. The geometry of the sky, the size of its ripples, the tilt of its spectrum, all are messages from that earlier era, translated into the language of light. The echoes of inflation are not loud. They are subtle, embedded in temperature differences of millionths of a degree, in polarization patterns that require years of observation to detect. Yet they speak across 14 billion years of cosmic history, carrying the memory of a moment that lasted less than a trillionth of a second. The contrast between brevity and consequence is what makes inflation so remarkable. It was a brief silence that set the rhythm for everything that would follow, and as the universe continued to expand and cool, the light that carried those echoes began its long, unbroken journey. It would pass through the forming galaxies, through the growing cosmic web, through clusters of stars and the darkness between them. It would keep travelling, losing energy to expansion, shifting to longer wavelengths, cooling but never ceasing. Even now that same ancient light reaches us, bearing the faint, persistent imprint of the universe's first expansion. In that light, the universe tells its story of how infinity took shape, how flatness was achieved, and how the smallest quantum fluctuations became the structure of everything. Inflation may have ended long ago, but its resonance remains. Every measurement, every map, every photon of the cosmic microwave background is one more echo from that moment, still crossing the silent geometry of space, still carrying the trace of the universe's earliest breath. The light that fills the universe carries more than warmth and memory. It carries direction. Every photon that has crossed the cosmos since those first moments of transparency has an orientation, a subtle alignment imprinted upon it by the forces it met along the way. This alignment, this polarization, is one of the quietest and most revealing signatures in the cosmic microwave background. Within its delicate patterns lie hidden clues, messages about the early universe, about gravity itself, and perhaps about the faint tremors of space-time left behind by inflation. When we talk about polarization, we usually think of sunglasses or camera filters that block certain angles of light. Polarization simply describes the direction in which light waves oscillate as they travel. Ordinary light, like that from a lamp or a star, is unpolarized. Its waves vibrate in all directions, but under certain conditions light can become polarized, meaning the vibrations align more strongly in one direction. On Earth, sunlight becomes partially polarized when it scatters off molecules in the atmosphere. The same process occurred in the early universe, but on a cosmic scale. After recombination, when electrons and protons joined to form neutral atoms, the universe became transparent. Yet some photons still scattered off the remaining free electrons. When light scatters, its electric field can become aligned depending on the geometry of the interaction. If the radiation around an electron has equal intensity from every direction, there's no preferred alignment. But if the radiation is slightly uneven, if one direction is brighter or denser, the scattered light becomes polarized. That's what happened in the young universe. The same small fluctuations in density that created the temperature variations in the CMB also caused differences in the intensity of radiation arriving at each point. As photons scattered, those differences produced a faint but measurable polarization in the background light. The polarization pattern is incredibly subtle, thousands of times weaker than the temperature variations themselves, but it carries unique information. Where temperature fluctuations reveal the density and velocity of the early plasma, polarization traces the motion of that plasma and the geometry of the last scattering surface, the spherical shell from which the CMB photons last interacted. The orientation of the polarization tells us how matter was moving and how gravity shaped those motions. By mapping it, scientists can reconstruct the flow of the universe as it was nearly 14 billion years ago. Polarization in the CMB can be separated into two distinct types, E modes and B modes. The distinction comes from how the polarization pattern curls or doesn't curl across the sky. E modes, named by analogy to electric fields, form smooth, radial or circular patterns without any twist. They are produced primarily by density variations, the same acoustic oscillations that shape the temperature map. B modes, named by analogy to magnetic fields, form swirling, curl-like patterns. They require something more than simple density variations. The only known processes that can create B modes on large scales are gravitational waves or gravitational lensing, the bending of light by mass. E modes were detected first. In 2002, the Degree Angular Scale Interferometer, DESI, experiment in Antarctica, made the first successful measurement of polarization in the CMB. It confirmed a key prediction of cosmology, that the same sound waves responsible for temperature fluctuations also produced polarized light. Later missions, including DOMAP and Planck, mapped the E-mode polarization with extraordinary precision, showing that its patterns match exactly what theory predicts. The polarization peaks align with the temperature peaks in a way that reveals how radiation pressure and gravity interacted in the early plasma. It was another triumph of the Big Bang model, a quiet confirmation encoded in the angle of ancient light. The search for B modes, however, has been more elusive and far more profound. Detecting them would mean detecting the influence of primordial gravitational waves, ripples in space-time itself produced during inflation. Those waves would have stretched and squeezed space as they moved, subtly altering the polarization of the CMB photons passing through. The result would be a faint swirling pattern imprinted across the sky, a cosmic fingerprint of gravity's earliest motion. If found, it would be direct evidence that inflation happened, and that gravity behaves quantum mechanically at the highest energies. The difficulty is that B modes are incredibly faint. The signal is small enough that even the heat from surrounding instruments, or the emission from dust in our own galaxy, can easily obscure it. In 2014, the BICEP-2 experiment at the South Pole announced what looked like a detection. The data showed a pattern consistent with primordial B modes, and for a brief moment, the discovery seemed to confirm one of cosmology's greatest predictions. But further analysis revealed that much of the signal came from galactic dust, tiny grains of material aligned by magnetic fields, emitting their own polarized microwaves. Once that foreground contamination was removed, the evidence for primordial B modes disappeared. It was a reminder of how delicate these measurements are, and how easily the universe can hide its earliest truths behind its own complexity. Still, the search continues. The Planck satellite, working together with ground-based telescopes like BICEP-3, the South Pole Telescope, and the Atacama Cosmology Telescope, continues to refine polarization maps with increasing sensitivity. The goal is not only to detect the B-mode signal, but to separate its two sources, gravitational lensing and primordial waves. Lensing B-modes occur when light from the CMB is bent by massive structures, galaxies and clusters, on its way to us. This bending distorts the E-mode polarization, twisting it slightly into a B-mode pattern. By measuring that lensing signal, scientists can reconstruct the distribution of matter in the later universe. By subtracting it, they can look for the fainter primordial signal underneath. Even without a confirmed detection of primordial B-modes, polarization has already revealed a wealth of information. It has confirmed the timeline of recombination, the speed at which the universe became transparent, and the rionization that followed hundreds of millions of years later when the first stars and galaxies formed. It has refined our understanding of the universe's curvature, its expansion rate, and the proportion of ordinary matter to dark matter. The polarization map is like a second layer of the CMB, a more delicate but equally rich version of the same story. One of the most striking aspects of CMB polarization is how it allows scientists to trace the invisible. Gravity leaves no light of its own, but it bends and stretches the paths of light around it. The polarization patterns we observe today carry the marks of those distortions. By analysing them, cosmologists can reconstruct the large-scale structure of the universe, not by seeing galaxies directly, but by seeing how they warp the background light. This technique, known as CMB lensing reconstruction, produces a kind of gravitational map of the cosmos. It shows where matter, both visible and dark, lies between us and the surface of last scattering. In this way, the CMB becomes not only a picture of the past, but also a tool for mapping the present. Polarization also helps refine our understanding of rionization, the era when the first stars and galaxies formed and began to emit ultraviolet light, rionizing the hydrogen that had become neutral after recombination. As that process unfolded, the newly freed electrons once again scattered CMB photons, adding another layer of polarization at large angular scales. By measuring that additional signal, scientists can estimate when the first luminous structures appeared. The results suggest that rionization began roughly 400 million years after the Big Bang, a finding consistent with observations of the earliest galaxies. In this way, polarization connects the first light of the universe to the first light of stars. The hidden clues within polarization patterns go even deeper. Tiny deviations from randomness in the way polarization aligns across the sky could reveal new physics. Effects of primordial magnetic fields, signatures of parity violation, or evidence for topological defects like cosmic strings. So far, no such deviations have been confirmed, but the potential remains. Every improvement in sensitivity opens a new layer of the cosmic record, a new opportunity to read the fine print written in ancient light. The complexity of measuring and interpreting polarization is extraordinary. The signal itself is faint, but the noise, from our own atmosphere, from galactic dust, from the instruments themselves, is strong. Extracting truth from that noise requires years of careful observation, cross-correlation, and calibration. Yet the effort is worth it. Polarization is one of the few tools we have to peer into the universe's first instance. It bridges the visible and the invisible, the early and the late, the known and the unknown. There's something almost poetic in the idea that the universe, which began in brightness too intense for light to escape, now whispers its secrets in the angle of polarization. The same photons that once bounced endlessly within the primordial fog now carry with them a record of every encounter, every scattering, every distortion they experienced on their journey. In their orientation, we can read the story of the universe's expansion, its geometry, and its invisible scaffolding of gravity. When scientists create maps of the polarized sky, The result looks different from the temperature maps of the CMB. Instead of random patches of colour, they show a web of filaments and swirls, lines indicating the direction of polarisation at each point. It's a visual record of motion, of how matter moved and how light scattered billions of years ago. The patterns are intricate but consistent, like the grain of wood formed by cosmic forces. The geometry of those lines reflects the balance of radiation pressure and gravity at the time of last scattering. Each subtle twist and turn is a memory of the universe's earliest turbulence. As the universe expanded, the polarization patterns evolved slightly, distorted by the gravitational pull of forming structures. These distortions add another layer of information, a way to measure how matter has clustered over time. By comparing the original polarization pattern, as inferred from theory, to what we see today, scientists can trace the growth of structure from the CMB's release to the present. It's a continuous line of evidence stretching from the first light to the modern cosmos. Even now, polarization data continues to refine our understanding of fundamental physics. It provides limits on the masses of neutrinos, particles that interact so weakly that billions pass through us every second unnoticed. It helps test the constancy of physical laws, such as whether the fine structure constant, which determines how strongly light interacts with matter, has remained stable over cosmic history. It even constrains theories of dark energy, the mysterious force driving the universe's accelerated expansion. The clues are faint, but they accumulate, building a picture of the cosmos that grows sharper with every measurement. In the faint polarization of ancient light, the universe has hidden a record of its most delicate features. The direction in which photons oscillate tells us how matter moved, how gravity curved space, and how the first stars reignited the cosmos. It tells us that the same light which began its journey in perfect uniformity now carries the fingerprints of everything that ever disturbed it. The universe doesn't shout its history. It encodes it quietly, in the angle of its own radiation. And as those photons continue to travel, still stretching with the expansion of space, they pass through the large-scale structures they once helped to form. Clusters of galaxies, filaments of dark matter, and the expanding voids all leave their mark on the polarization patterns. The ancient light interacts gently with the modern universe, recording one last layer of information before reaching us. Every photon we detect has crossed billions of years of cosmic history. In its faint polarization, it carries both the memory of where it came from and the imprint of everything it passed through. The hidden clues are still being read. Each new observation adds resolution, removes noise, and refines what we know. And through it all, the light remains steady, a quiet, polarized echo from the time when the universe first became transparent. As we listen to that echo more carefully, we learn not only about the physics of creation, but about the persistence of information itself. The universe, it seems, forgets nothing. Even in its faintest glow, it remembers the shape of its own beginning. The universe, before it became transparent, wasn't silent. It couldn't have been. The sea of plasma that filled space in those first hundreds of thousands of years after the Big Bang was dense enough for sound to exist, though not the kind of sound we could ever hear. There was no air, no ears, no atmosphere to carry familiar vibrations, but there was matter, a vast mixture of protons, electrons, and photons, bound together by radiation pressure and gravity. In that thick, glowing fluid, pressure waves rippled outward, compressing and rarefying as energy moved through it. The cosmos was, in its own way, ringing. What we call the cosmic soundtrack is not something we could play through speakers or record with a microphone. It exists as a pattern of density fluctuations, fossilized in the cosmic microwave background. The ripples that once passed through the early plasma froze in place when the universe became transparent. Those vibrations, though long stilled, left their mark in the faint temperature variations we measure today. By analysing the spacing and strength of those variations, scientists can reconstruct the rhythm of the early universe. Each peak and trough in the CMB's power spectrum corresponds to a note in that ancient song. Sound in the early universe worked through balance, the push and pull between gravity and radiation. Gravity tried to draw matter together, forming dense regions. Radiation pressure, driven by the intense photons trapped in the plasma, pushed outward, resisting collapse. The two forces created oscillations, compression followed by rarefaction, like the vibration of a string or the beating of a drum. Every fluctuation in density was a pulse, a sound wave travelling through the medium of the cosmos. These waves moved at about half the speed of light, carrying information and energy across vast distances. The first oscillations began almost immediately after inflation ended, when the universe was still a hot, dense field of plasma. Quantum fluctuations, stretched to macroscopic scales by inflation, provided the initial irregularities in density. Those irregularities triggered gravity's pull, compressing matter in some regions more than others. The compressed regions grew hotter and denser, causing radiation pressure to push outward. When that outward force overcame gravity, the region expanded, cooled, and then gravity took over again. It was a cosmic rhythm, a steady oscillation repeating across all of space. These oscillations continued for hundreds of thousands of years. Because light was trapped within the plasma, every movement of matter was tightly coupled with radiation. Photons acted as a spring, restoring balance whenever gravity compressed too far. The result was a series of standing waves, pressure patterns that didn't travel freely but oscillated in place, like the resonant modes of a musical instrument. Different regions of the universe vibrated with different frequencies, depending on their size and density. The superposition of all these vibrations created the cosmic soundtrack, not audible, but mathematically precise. When the universe finally cooled enough for atoms to form and photons to decouple, these oscillations froze. The pressure stopped. The plasma became a transparent gas. The sound waves could no longer propagate because the medium no longer supported them. But the imprint of those vibrations remained. The peaks of compression and expansion left permanent marks in the temperature of the radiation. Those marks are what we see in the CMB as alternating regions of slightly higher and lower temperature. The CMB's power spectrum, the graph showing how temperature fluctuations vary with scale, is the closest thing we have to a recording of those sounds. The first peak represents the largest mode of oscillation, the fundamental frequency of the universe's early vibrations. Subsequent peaks correspond to harmonics, waves that oscillated multiple times before the universe became transparent. By measuring their spacing and amplitude, cosmologists can deduce the composition and properties of the early universe with remarkable precision. For instance, the relative height of the first and second peaks tells us the ratio of ordinary matter to dark matter. The presence of dark matter changes how strongly gravity pulls on the plasma, affecting the balance of compression and expansion. The third peak provides information about the density of baryons, protons and neutrons, and about the overall curvature of space. Each feature of the spectrum corresponds to a physical property, making the cosmic soundtrack a detailed diagnostic of the universe's birth conditions. When scientists translate those oscillations into sound frequencies, the results are eerie and beautiful, though vastly slowed down from their original speed. The fundamental tone of the early universe was far too low for human hearing. With wavelengths spanning hundreds of thousands of light years, the frequencies were on the order of 10 to the minus 12 Hz. But if scaled up into an audible range, the universe's first song would sound like a rising hum, a complex chord of overlapping notes resonating through the expanding cosmos. It's worth remembering that this sound isn't metaphorical. It's a physical oscillation of pressure and density. The same mathematics that describe acoustic waves in air describe the oscillations in the early plasma. The universe truly did vibrate, and those vibrations, though long frozen, remain visible to us in the structure of the CMB. The universe was, for a time, not only filled with light, but filled with resonance. The acoustic oscillations didn't just shape the CMB, they also influenced the later distribution of galaxies. The same patterns that formed in the plasma before recombination left their imprint on the matter that followed. As the universe expanded and cooled, those imprints guided how matter clustered. Even today we can see their legacy in the large-scale structure of galaxies. The distances between clusters often show a preferred scale, a faint regularity known as baryon acoustic oscillations, or BETO. These are the echoes of those primordial sound waves, stretched and frozen into the distribution of matter itself. By measuring BETO in galaxy surveys, scientists can track how the universe has expanded over billions of years. That continuity, from pressure waves in a plasma to the arrangement of galaxies, is one of the most elegant threads in cosmology. It means that the same physics governing the earliest universe continues to shape it now. The ripples in the CMB and the structure of the cosmic web are parts of the same melody, played across different epochs of time. The rhythm of the early cosmos is still visible in the way galaxies gather in filaments and clusters. The discovery of these acoustic patterns in both the CMB and galaxy distributions has provided one of the strongest confirmations of the standard cosmological model. It ties together observations separated by billions of years and billions of light years. The consistency between the CMB's power spectrum and the BETO measurements demonstrates that the universe has evolved predictably under the influence of gravity, expansion, and dark energy. The cosmic soundtrack is more than a metaphor. It's an experimental link between the earliest vibrations and the modern sky. Each mode of oscillation tells us about a specific balance between forces. The first peak, corresponding to the larger scales, represents regions that had time to complete just one full oscillation before recombination, one compression and one expansion. The second peak represents regions that oscillated twice, and so on. The relative strength of these peaks tells us how strongly radiation pressure resisted gravity, and how much matter was present to drive the oscillations. In this way, the universe's first vibrations reveal not only its composition, but its dynamics, how quickly it expanded, how hot it was, and how it cooled. The simplicity of the physics makes it all the more profound. The universe began as a nearly uniform field of energy. Small irregularities, amplified by gravity and pressure, produced oscillations. Those oscillations set the initial conditions for structure formation. From them, galaxies, stars, and planets emerged. The laws of acoustics, the same principles that govern the vibration of air in a flute or strings on a violin, shape the evolution of everything we see. The cosmos, in that sense, is an instrument, and the CMB is its first note. Even now, the remnants of those oscillations continue to inform our understanding of cosmology. When scientists measure the angular size of the first acoustic peak in the CMB, they use it as a standard ruler. Because we know the physical size of the sound horizon at recombination, we can compare it to the apparent size on the sky to determine the universe's geometry. The result confirms, again, that space is flat. The same oscillations that once produced sound now serve as a cosmic measuring tool. The presence of these harmonics also rules out alternative cosmological models. No other theory produces the specific repeating pattern of peaks observed in the CMB. The acoustic signature is unique to a universe that began in a hot, dense state and evolved under the influence of gravity and radiation. It's as though the cosmos left behind a perfect fingerprint of its own history, encoded in a pattern of waves. The precision of this fingerprint allows scientists to measure parameters with extraordinary accuracy. We know the age of the universe, 13.8 billion years, primarily from the shape of the CMB's power spectrum. We know the relative amounts of dark matter and dark energy from the heights and positions of its peaks. We even know how fast the universe was expanding when it was only a few 100,000 years old. All of that information comes from the frozen echoes of sound. It's difficult to imagine that such vast knowledge could emerge from something as intangible as pressure waves. Yet that's the beauty of physics. Simple principles, extended across unimaginable scales, can explain the grandest patterns of nature. The universe's first music wasn't composed of matter, but of motion, the movement of energy through space and time. And though we can no longer hear it, we can still see its trace in the faint speckled glow that fills the sky. If we could somehow travel back to that early era and immerse ourselves in the plasma, the experience would be beyond comprehension. The entire universe would appear as a bright, glowing fluid, opaque and radiant. Everywhere, matter would be in motion, rising and falling in enormous waves. The scales of those waves would dwarf anything imaginable. Crests and troughs spanning hundreds of thousands of light years, oscillating in slow motion compared to the heartbeat of a human lifetime. The sound would not be sound as we know it, but pressure, a continuous resonant vibration of the medium itself. When the universe became transparent, those waves stopped propagating, but they did not vanish. The last snapshot of their motion became the CMB we observe today. The pattern of temperature fluctuations is a frozen image of sound, the final frame of a vibration that played for hundreds of thousands of years. Every hot and cold spot on the sky corresponds to a phase of those oscillations. The cosmic soundtrack ended abruptly, but its echoes continue forever. The very existence of these oscillations provides yet another confirmation of the Big Bang model. If the universe had always been cold and static, there would be no mechanism for such coherent vibrations to exist. The presence of acoustic peaks in the CMB proves that the universe was once hot, dense, and filled with tightly coupled matter and radiation. The sound waves are the direct consequence of that coupling, the audible, or rather visible, memory of a time when light and matter were inseparable. Even the way those waves decay tells a story. As the universe expanded, the amplitude of the oscillations diminished. The energy of each wave was spread across an ever-growing volume of space. The frequency of the waves decreased as the density dropped. The rhythm slowed. Eventually, as atoms formed and photons decoupled, the music stopped altogether. But the silence that followed wasn't empty. It was filled with potential. The potential for matter to condense, for light to travel, for the universe to become visible. The end of sound was the beginning of structure. What we call silence now is, in truth, a continuation of that same process. The expansion of space has stretched the wavelengths of those ancient vibrations to such enormous scales that they're no longer waves in the usual sense. They've become the scaffolding of the universe's large-scale structure, the framework upon which galaxies formed. The cosmic soundtrack never truly ended. It simply transformed, slowing its rhythm until it became imperceptible, leaving only the geometry and distribution we see today. When cosmologists plot the CMB's acoustic peaks, they're not just measuring temperature. They're reading the score of that ancient music. Each peak is a note, each trough a pause, and together they form the melody of the cosmos's first era. The fact that the data fits the theory so precisely, that the peaks occur exactly where the equations predict, is one of the most extraordinary achievements of modern science. It shows that the universe's first song was not random noise, but a coherent, measurable symphony governed by physical law. Even the slight deviations from the perfect pattern hold meaning. The small differences in amplitude between peaks reveal the presence of dark matter, which influenced how the waves evolved. Without dark matter's gravitational pull, the oscillations would look different. In this way, the cosmic soundtrack is also a record of the unseen. The invisible matter that makes up most of the universe revealed itself through its influence on the earliest vibrations. The cosmic soundtrack continues to guide us in other ways too. By comparing the CMB's acoustic peaks with those found in galaxy surveys, scientists can test whether dark energy has changed over time. If the expansion of the universe had varied differently, the spacing of the peaks in the matter distribution would not align with those in the CMB. So far, they match perfectly. reinforcing the idea that the same dark energy driving the universe today has been constant for billions of years. The early universe's sound waves thus connect directly to the modern universe's acceleration, an unbroken link between the first vibrations and the expanding cosmos we live in. The universe no longer resonates in the way it once did, but its structure still carries the memory of its original harmony. The sound waves that shaped the plasma became the patterns that shaped the stars. The same physics that made the cosmos sing now determines how galaxies cluster, how light bends, and how time itself unfolds. The rhythm of the early universe has become the pattern of the present one, and as we continue to listen, through telescopes, detectors, and the mathematics of the CMB, the universe keeps offering new verses of that ancient song. Each measurement reveals another layer of resonance, another chord in the grand composition of cosmic history. The light we study is silent, but what it carries is music, not of air, but of space itself, vibrating once in a long-forgotten dawn and still echoing in the faint hum of the oldest light in the sky. The light that fills the universe doesn't just show where we came from, it shows what we are made of. The cosmic microwave background, faint and ancient as it is, acts as a mirror, one that reflects not our image, but our origins. When scientists study that light, they are looking into a reflection of the universe's composition, its balance of matter and energy, its subtle imperfections that became everything familiar. The CMB is not only a photograph of the past, it's a precise record of the ingredients and proportions that shaped existence itself. When we look into that mirror, we see that the universe is built mostly from things we cannot see. The light tells us that only about 5% of everything is ordinary matter, the kind that makes up atoms, planets, stars, and us. The rest, more than 95%, is invisible. Roughly 27% is dark matter, an unseen form of mass that interacts through gravity but not light. The remaining 68% is dark energy, a mysterious force that drives the universe's accelerated expansion. These numbers come directly from measurements of the CMB, the pattern of ripples, the heights of the acoustic peaks, and the overall curvature of space combine to reveal the cosmic recipe. It is astonishing that from the faint afterglow of creation, we can deduce the invisible architecture of reality. The way this information emerges is rooted in physics as simple as it is profound. When the universe was young, all forms of matter and energy interacted with each other. The density of each component affected how sound waves move through the plasma. More ordinary matter meant stronger compression, which altered the amplitude of certain peaks in the CMB's spectrum. More dark matter changed the gravitational potential wells that those sound waves oscillated within. And the presence of dark energy, though insignificant at that early time, determined the universe's overall geometry, subtly influencing the scale of the observed fluctuations. By fitting the observed power spectrum to models based on these principles, scientists can infer the relative amounts of each component. The CMB doesn't just show light, it reveals composition. The proportions it reveals are not arbitrary. They define how the universe evolved, how galaxies formed, how stars were born, and even how long it took for life to appear. If there had been slightly more ordinary matter, the universe would have collapsed under its own gravity before it could cool. Slightly less, and structures would never have formed at all. The balance we observe is delicate, the result of physical laws operating with remarkable precision. In that balance, written in the pattern of ancient radiation, we find the reflection of everything that would one day look back at it. To understand why these numbers matter, imagine the early universe again, a dense, hot mixture of matter and radiation. In that environment, the density of dark matter determined how deep the gravitational wells were, the places where matter would begin to collect. Dark matter doesn't interact with light, so while the photons pushed against the baryons, the ordinary matter, dark matter simply waited, unmoved by radiation pressure. It gathered silently, forming the invisible scaffolding upon which visible structures would later form. When the photons finally decoupled at recombination, the baryons began to fall into those dark matter wells, pulled by gravity into the first seeds of galaxies. This CMB shows us those seeds, the places where dark matter had already begun to shape the future. The light from that moment carries a signature of these interactions. Regions with more matter show slightly higher temperatures because photons had to climb out of deeper gravitational wells, losing energy in the process. This subtle effect, known as the Sachs-Wolf effect, adds another layer of information to the CMB's pattern. By studying it, scientists can measure the strength of the gravitational potential at the time of recombination, a direct window into the distribution of dark matter. Even though we can't see dark matter directly, we can see its shadow in the way it shaped light. This mirror of origins doesn't stop at matter. It also reveals the nature of the universe's earliest expansion, the small tilt in the spectrum of fluctuations, the fact that there is slightly more power on large scales than on small ones, tells us that the initial perturbations came from inflation. That tiny tilt, known as the scalar spectral index, measures how quantum fluctuations were stretched across the cosmos. Its value, around 0.96, matches what inflationary models predict for a universe that expanded exponentially. The CMB is therefore both a reflection of the universe's composition and a confirmation of its earliest dynamics. When we interpret the CMB as a mirror, what we see is not just the physical matter that fills the universe, but the relationships between its components. The ordinary matter, dark matter, and dark energy are not separate entities. They interact through the geometry of space-time. The proportions the CMB reveals are the parameters that define that geometry. They determine how fast the universe expands, how structures grow, and how light travels through it. In this sense, the CMB is not a static image, but a map of interdependence, a record of how everything affects everything else. The reflection also shows us something about time itself. The uniformity of the CMB across the sky means that the universe's earliest moments were in near-perfect thermal equilibrium. That equilibrium could not have happened without inflation, which expanded a small, uniform region to cosmic scales. But the slight imperfections, the tiny ripples in temperature, are what allowed time to move forward in a meaningful way. Without differences in density and energy, there would be no gradients to drive motion, no structure to evolve, no entropy to increase. In those imperfections, the universe gained its arrow of time. The CMB shows not only where we came from, but how time itself began to unfold directionally. It's strange to realize that the same light that reveals the origins of matter also reveals the conditions that made memory possible. The asymmetry between uniformity and difference is what allows the universe to change. Every fluctuation in the CMB is a record of that asymmetry, a small imbalance that set the flow of time into motion. When we measure those fluctuations, we're not just looking back. We're watching the first distinction between before and after. The mirror of the CMB reflects other aspects of ourselves too. The atoms in our bodies, the carbon, nitrogen, oxygen and iron, were forged in stars that descended from the first structures seeded by those fluctuations. The same gravity that amplified those early ripples eventually gathered hydrogen into dense clouds, igniting nuclear fusion and creating the elements of life. The process took billions of years, but its foundation was laid in the pattern of the CMB. The map of temperature variations, subtle and precise, determined where galaxies would form, how they would cluster, and where stars would live and die. In a very literal way, our existence is written into that light. It's not only matter and structure that the CMB reflects, it also reveals how energy itself behaves on the grandest scales. The way the CMB cools as the universe expands, its temperature decreasing steadily over time, follows the same thermodynamic laws that govern everything from steam engines to stars. The radiation has cooled from roughly 3000 Kelvin at recombination to just 2.725 Kelvin today. This exact temperature, measured with exquisite precision, confirms our understanding of how expansion stretches wavelengths and lowers energy. The CMB's temperature is a direct measure of the universe's age and scale. When scientists first measured this background temperature in the 1960s, they were confirming not just a theory, but a prediction of remarkable accuracy. The light's current temperature matches what we expect from a universe that has expanded by a factor of roughly 1,000 since recombination. Every photon we detect has been stretched to a wavelength 1,000 times longer than it was when it was emitted. This stretching is what turns visible light into microwaves, and it's the same mechanism that cools the radiation. The mirror shows us, in its faint glow, the direct consequence of expansion itself. That same expansion continues today, driven by dark energy. The acceleration of the universe, discovered in the late 1990s through observations of distant supernova, was already anticipated by the balance revealed in the CMB. The flatness of space, the composition of energy, and the rate of expansion all align perfectly with a universe dominated by dark energy. This connection between the earliest and latest epochs, between the CMB's smooth background and the modern universe's accelerating growth, is one of cosmology's great symmetries. The mirror doesn't stop at the past, it extends into the present. Every refinement of CMB measurements sharpens that reflection. With each new satellite, each new survey, we see the universe's face more clearly. The Planck mission, for instance, measured not only the temperature fluctuations, but also the polarization of the CMB with unprecedented accuracy. That polarization pattern adds depth to the reflection, revealing how the first light scattered and how later structures distorted it. In those distortions, we can see the gravitational influence of dark matter and the subtle lensing caused by galaxies and clusters. The CMB becomes, in effect, a mirror that shows both the distant past and the intervening history. What makes this reflection so remarkable is its universality. No matter where you are in the cosmos, if you could observe the microwave background, you'd see nearly the same pattern. The same ripples, the same proportions, the same faint temperature of 2.7 Kelvin. That uniformity is not an illusion. It's a property of space itself. Every observer in the universe, no matter how distant, sees their own version of the same cosmic mirror centered on themselves. There is no privileged position. The universe reflects itself equally in all directions. This fact, that the cosmos looks the same from every point, carries a profound implication about our place within it. It means that we are not observers outside of the universe looking in, but participants within it, seeing from one point in an infinite field of equal points. The light we receive is both personal and universal. It reaches us specifically, but it carries the same message to everyone, everywhere. The cosmic mirror shows us that we are both insignificant in scale and essential in connection. We exist within the same pattern that defines everything else. Even the imperfections in the CMB's pattern, the tiny random deviations from uniformity, tell us something about probability and origin. They are consistent with what's called a Gaussian random field, meaning they follow a specific statistical distribution. This randomness is not chaos. It's structure born from quantum fluctuations. The same mathematics that describe randomness in quantum systems describe the irregularities in the CMB. The mirror shows not a perfect face, but a natural one marked by variation, symmetry, and chance. Some scientists have searched for anomalies in this reflection, features that might reveal something unexpected. A slight asymmetry between one hemisphere and the other, a cold spot larger than statistical models predict. A possible alignment of temperature patterns across wide areas of the sky. Each of these has sparked debate. Are they signs of new physics, or just coincidences in a random field? The data remains inconclusive, but even these anomalies, whether real or imagined, remind us that the universe's reflection is not a static picture, but a living, interpretable pattern. Every pixel invites interpretation, every variation a hypothesis. Looking into the CMB's mirror is unlike looking into any other kind of reflection. It doesn't show a surface, it shows a depth of time. Each photon we detect has travelled for nearly 14 billion years. It left the surface of last scattering when the universe was young and has been stretched, bent, and redshifted ever since. When we measure its direction and energy, we are receiving information from that exact moment in the past. The sky above us, glowing faintly in microwaves, is a spherical shell of ancient history. We are surrounded by it. Every direction is the past. Every photon is a piece of our origin. What's most striking is how familiar this process feels, even though it deals with scales far beyond human experience. We look into mirrors every day to understand who we are, yet those reflections only show the surface. The CMB is a mirror of a different kind, one that shows structure beneath structure, pattern beneath form, cause beneath consequence. It shows how light and matter, energy and space, chance and necessity combine to make everything we know. The mirror doesn't show us our faces. It shows us why faces exist at all. That faint glow, that quiet background radiation still passing through us every moment, is not just a relic of the Big Bang. It's a continuing presence, a reminder of the universe's constant expansion and memory. It tells us that nothing in the cosmos is ever truly lost. Every photon carries the story of where it's been. Every interaction leaves a trace. The CMB is the sum of those traces, the universal archive of beginnings. And as that light continues its journey, moving ever outward through space, it keeps reflecting new things. The gravitational pull of clusters, the faint distortions of lensing, the slow red shifting of cosmic expansion. Each of those effects adds another layer to the reflection, another clue about how the universe evolves. The mirror keeps changing, even as its image remains ancient. Soon, that same light would bring us to the edge of visibility itself, to the limit of what can ever be observed. Beyond it lies only darkness, not because there is nothing there, but because the light from those regions has not yet had time to reach us. The cosmic mirror shows not only where we came from, but also where the boundary of knowledge stands. Beyond that boundary, space continues, silent and invisible. The light we have is enough to see just far enough to understand what lies beyond imagining. The light from the beginning is still arriving. Every second, every minute, every hour, the oldest photons continue their slow descent through expanding space, crossing distances so vast that human language struggles to contain them. When we study that light, we are not merely observing the past, we are witnessing it in the present. Each photon of the cosmic microwave background is a messenger from a time when atoms first formed, carrying with it the conditions, temperature and texture of that moment. Looking into that radiation is not like looking far away. It's like looking back through time itself. To gaze into the cosmic microwave background is to confront the limit of what can ever be seen. Beyond that light lies a wall of opacity, a time before transparency, when photons could not travel freely. The CMB marks the surface of last scattering, the boundary between the visible universe and the unobservable past. It is, quite literally, the edge of sight. Every telescope, every detector, every experiment designed to capture ancient radiation is aimed not into a region of space, but into a period of time. The further we look, the earlier we see. That simple principle, that distance corresponds to age, defines modern cosmology. Light takes time to travel, and the universe has been expanding all the while. The farther away a source is, the older its light. Galaxies a few million light years distant show us the recent past. Galaxies billions of light years away show us the early universe. But the cosmic microwave background stands beyond them all. It is the farthest light there is, the oldest information that can ever reach us. To gaze upon it is to see the universe as it was just 380,000 years after its beginning. In a way, the CMB is both the beginning and the limit of vision. anything that existed before recombination is hidden, not because it didn't exist, but because light couldn't escape. The plasma that filled the early universe was so dense that photons scattered endlessly, bouncing off free electrons without ever travelling far. Space was filled with brightness, but it was brightness without direction. Only when atoms formed, freeing the photons to move unhindered, did that brightness take shape as radiation that could travel, radiation that we can still detect today. Every observation we make of the CMB is a direct measurement of that moment of release. The photons we collect now left their points of origin nearly 14 billion years ago and have been travelling ever since. The universe has expanded roughly 1,000 times during their journey. Their wavelengths have stretched from visible light to microwaves, their energy reduced, their colour faded, but their information intact. Each one carries a record of temperature, density and motion from the dawn of transparency. When we map the CMB across the sky, we are effectively creating a three-dimensional picture projected onto a sphere around us. That sphere represents the edge of the observable universe, the distance light could have travelled since the Big Bang. Inside that sphere lies everything we can see: galaxies, clusters, dark matter and the cosmic web. Beyond it lies the unobservable region, expanding still, unreachable, because light from there has not yet had time to arrive. The CMB is the outer boundary of sight, the visible surface of time. The photons that form this boundary don't arrive evenly. They come from every direction, filling every cubic centimetre of space with an average of about 400 photons. Every second, trillions of them pass through our bodies, our planet, our atmosphere. They are everywhere, all the time, indifferent to matter and gravity. Most have not interacted with anything since they were first released. They are perfect messengers, silent, tireless, unchanged. What makes gazing back through this radiation so extraordinary is the precision with which we can read it. The faint variations in its temperature, measured in microkelvins, reveal the seeds of all cosmic structure. The geometry of its patterns reveals the curvature of space. The distribution of its peaks reveals the composition of matter and energy. The polarization of its light reveals the motion of the early plasma, and even hints of gravitational waves from inflation. Every detail, every subtle fluctuation, is a clue. A data point in the reconstruction of the universe's entire history. When scientists look at the CMB, they aren't seeing an image in the ordinary sense. They're seeing a record of physical processes frozen in time. Each variation in brightness corresponds to a density contrast, a small difference in temperature that reflects how matter and energy interacted before light could escape. The photons themselves are not static. They've been stretched and deflected by the structures they've passed along the way. The light we see is not only ancient, but also altered by the entire history of the universe between then and now. The galaxies, clusters, and filaments that formed later all leave faint imprints on the background through gravitational lensing and other effects. In the CMB, we see both the first moment of visibility and the integrated record of everything that has happened since. To gaze into this light is to see the universe layered in time. The foreground shows the present, our galaxy, our stars, our dust, our cosmic neighbourhood. Behind that lies the distant distribution of galaxies, clusters and voids, and behind it all, the CMB, glowing faintly, the background to everything else. Each layer is another step backward, another chapter in the same story. The light itself becomes the timeline, stretching from now to the very beginning. This connection between distance and time changes how we understand space. What we call out there is, in cosmological terms, back then. The further out we look, the earlier we see. Every photon that reaches us began its journey billions of years ago, when the universe was smaller, denser, and hotter. The night sky is a map, not of space alone, but of history. Every point of light is a relic of a different era. The CMB is simply the oldest of those relics, the first image in the cosmic sequence. The remarkable thing about this image is its consistency. The temperature of the CMB is nearly the same in every direction, uniform to 1 part in 100,000. That uniformity tells us that the universe was already in near-perfect equilibrium when it became transparent. Yet the small deviations from that uniformity, the ripples and fluctuations, are what give the universe its structure. The balance between sameness and difference, smoothness and irregularity, is what defines everything that followed. In those slight imperfections, we can trace the path from the formless to the formed. To understand what it means to look back through time, imagine the universe as a vast sphere expanding in every direction. The further a photon travels, the more the universe expands while it moves. Its wavelength stretches with space itself, its energy diminishes, and its temperature cools. What we see today as microwave radiation was once visible light, shining from a universe filled with plasma. The journey of those photons has been relentless. No rest, no interruption, just an unbroken flight across an expanding cosmos. The moment they reach our detectors, their story completes, and the universe's story begins again through us reading it. The scale of this journey defies normal comprehension. Each photon has travelled about 46 billion light-years from its point of origin, even though the universe is only 13.8 billion years old. This is because space itself has expanded while the light travelled. The photons have not moved through a fixed void. They have ridden the wave of expansion, their wavelengths stretched by the same process that stretches galaxies apart. They are witnesses not only to time, but to the changing shape of space itself. Every telescope that studies the CMB, from Kobe to Map to Planck, is, in essence, a time machine. It collects ancient light and translates it into data, which we then reconstruct into an image of the universe's infancy. The detectors aboard these missions are designed to sense differences as small as millionths of a degree. The signals are faint, often buried beneath noise from our own galaxy, yet when cleaned and calibrated they reveal the pattern of the primordial universe. In those patterns, cosmologists find answers to questions that reach across billions of years. How old is the universe? What is it made of? How did structure form? How fast is it expanding? All of these answers come from that one layer of light. Looking at the CMB is, in this sense, the purest form of seeing possible. There is no reflection, no scattering, no secondary illumination. The photons we detect are the same ones that left the early universe unimpeded. They have not bounced off surfaces or refracted through lenses. They have simply travelled straight and free since the dawn of transparency. When they strike a detector, they carry information untouched by anything except time. The experience of seeing such light is different from seeing ordinary light. When we observe a star, we see an event that has happened in the past, but one that continues. The star still exists, still emits. When we observe the CMB, we see an event that has finished. The surface of last scattering no longer exists as it did. It's a boundary that moves away from us as the universe expands. Every moment we observe it, we are looking at a new shell of time, a slightly different horizon. The CMB is not static. It's an ongoing echo. We're always seeing it as it was 13.8 billion years ago, but it keeps receding, carried outward by expansion. The fact that we can measure this with such precision shows how consistent the laws of physics are. The same principles that describe light scattering in a laboratory describe light scattering across the universe. The same thermodynamic equations that apply to a gas in a container apply to the plasma that filled all of space. Time and scale change, but the rules remain constant. The CMB, in its faint uniformity, confirms that the universe is lawful, that the same processes hold everywhere and everywhen. As we continue to refine our instruments, the view grows sharper. We now map not only temperature variations, but also polarization patterns, gravitational lensing effects, and subtle distortions caused by intervening structures. Each of these adds depth to the image, like layers of paint revealing hidden texture. The more we observe, the more the CMB becomes not just a flat surface but a window, one that shows both the universe's beginning and its ongoing evolution. Gazing back through time has always been part of human curiosity. Long before anyone understood what stars were, people looked up and wondered if they were seeing the past. The night sky, though unchanged in appearance, always hinted at something deeper, a delay, a distance, a history. The discovery of the CMB gave that intuition scientific form. We now know that every glance into the heavens is a look into an earlier era. The faint microwave glow that pervades space is simply the farthest instance of that truth, the ultimate horizon of memory. There's an irony in how we perceive it. The CMB is everywhere, filling every direction, yet it's invisible to our eyes. We need antennas, detectors, and algorithms to reveal it. If our senses could perceive microwaves, the night sky would not be black. It would glow faintly with a uniform warmth, the same in all directions. Every horizon would shimmer with the relic light of creation. The darkness we see is not emptiness but blindness, a limit of our biology, not of the universe. The act of gazing back through time changes how we think about the present. It reminds us that the world around us is not static. Every photon of light we see, even from nearby sources, carries a delay. The moon appears as it was 1 second ago, the sun as it was 8 minutes ago, the nearest stars as they were years ago. Everything we perceive is slightly out of date. The CMB is simply the farthest extension of that delay, a view so old that it reveals the beginning itself. In a sense, we never see the present at all. We live entirely within the light of the past. This realization isn't abstract, it's direct. The microwave radiation that fills space is literally passing through us right now. Each photon that hits a detector in a lab or observatory has passed through galaxies, voids, and eons to arrive here. In their faint signal is the record of that entire journey. When we measure them, we're interacting with the oldest relics in existence. They are the closest thing to physical time travel the universe allows. The boundary defined by the CMB is not the end of the universe, only the end of sight. Beyond it, matter and energy continue, but the photons from those regions cannot yet reach us. As the universe ages, that horizon grows. More light will arrive, revealing new layers of the past. Yet there will always be a limit, a distance beyond which we can never see, not because of obstacles, but because of the finite speed of light and the constant expansion of space. The CMB marks that cosmic horizon. It's the farthest light we can receive and the deepest past we can witness. And yet even this limit is not final in spirit. The same laws that describe what we see in the CMB also describe what lies beyond. We can model the earlier universe, the period of inflation, the quantum fluctuations, the rise of structure, with remarkable accuracy, even without direct light from those epochs. The CMB serves as a translation surface, converting the unobservable into the measurable. Through it, we infer everything before light existed. It's not just the edge of vision, it's the bridge to understanding what lies beyond vision. Gazing back through time, through that endless radiation, we see not just the past of the universe, but the continuity of everything within it. Every atom, every element, every structure owes its existence to what that light reveals. The photons we detect today left their origins long before the Earth formed, long before the Milky Way took shape, long before any star burned hydrogen. They have crossed the entire history of everything. To detect them is to touch time itself, to feel the persistence of the beginning woven into the fabric of the present, and beyond this horizon of sight, beyond the faint cooling radiation that marks the edge of vision, the story continues unseen. The light that once filled all of space will keep fading, stretching to longer wavelengths, cooling further as the universe expands. But its message will remain the same. Every photon, no matter how faint, carries the memory of where we came from and the echo of where we are going. The light that began in brilliance, that dimmed into the faintest glow, still travels onward, reminding everything it touches that it was once part of a single, blinding dawn. The journey of those photons is not over, and neither is the story they carry. Ahead lies more darkness, but within that darkness the same light will continue to flow, still cooling, still spreading, still whispering of the first moment when the universe became visible, and still connecting us to it across the vast expanse of time. The light that began in the first moments of the universe has never stopped travelling. It has crossed every epoch, every transformation, every rearrangement of matter that has ever occurred. The photons that make up the cosmic microwave background were released when the universe first became transparent, and they have been on their way ever since. Each one carries the memory of that moment, of temperature, of motion, of the faint ripples that would one day become galaxies. They have crossed the birth of stars, the formation of galaxies, the slow drift of clusters, the quiet acceleration driven by dark energy. They are still here, still moving, still cooling, still fading, but never gone. The universe changes, but the light remains. Its temperature continues to drop as space expands, its wavelength stretching to longer and longer scales. From a fiery glow of thousands of degrees, it has cooled to less than 3 above absolute zero. Eventually it will cool even further, its photons stretched until their energy is so low that they become nearly impossible to detect. Yet they will still exist, filling space, carrying the faint imprint of the universe's beginning. The light will never fade completely. It will only grow gentler, its presence more subtle. The cosmic microwave background is a quiet witness. It has seen everything the universe has done and carries the trace of every force that has ever acted upon it. When it first escaped from the fog of the primordial plasma, the universe was just beginning to take shape. The photons spread outward, filling the expanding space evenly, carrying the last energy of recombination. As matter began to clump into clouds and stars, that light passed by, indifferent but observant. It passed through the cosmic dark ages, when there were no stars, only hydrogen gas slowly cooling in the dark. It passed through the era of reionization, when the first stars reignited the cosmos and made it transparent again. It passed through the rise of galaxies, the collision of clusters, the slow emergence of order. It crossed every transformation that time could offer, untouched, yet subtly altered by the gravity and structure it encountered. Every now and then, those photons encounter something massive enough to bend their path. Gravity, as Einstein showed, curves space itself, and light follows those curves. When a photon from the CMB passes near a galaxy or cluster, its trajectory bends slightly. The pattern of the background becomes distorted, stretched, or lensed by the matter in between. These distortions are faint, but measurable. They allow cosmologists to reconstruct the distribution of dark matter, to see how invisible structures shape the visible universe. In this way, the ancient light continues to teach us not just about the past, but about everything that has happened since. Some of the photons lose a little energy when they pass through regions of intense gravity. Others gain a little, depending on the motion of the matter they encounter. These shifts are small, but they add subtle details to the pattern of the CMB. The effect is like static in an old recording, where every scratch or fluctuation tells you something about what the sound passed through. The universe is full of that static, small imprints left by clusters, filaments, and voids. The photons carry all of it. They are still the same light that left the early universe, but their long journey has given them layers of memory. The remarkable thing about this light is how perfectly it describes the laws of physics. Every aspect of it, its temperature, its spectrum, its uniformity, its fluctuations, matches theoretical predictions to extraordinary precision. The CMB is a nearly perfect black body, meaning its spectrum follows the same curve that describes the radiation from any ideal emitter. That curve, defined by Planck's law, is one of the most fundamental in physics. The CMB fits it exactly, with no measurable deviation. This perfection shows that the early universe was in thermal equilibrium, a single smooth state of matter and radiation, balanced and consistent across all of space. To measure that perfection in light billions of years old is to confirm that the laws of thermodynamics, the same ones that govern stars and engines, have held unbroken since the beginning. Yet within that perfection lies texture. The tiny deviations from uniformity, 1 part in 100,000, are what gave the universe its character. Without them, there would be no structure, no stars, no life. The light that never fades is also the light that remembers those imperfections. It carries the record of randomness that became order, of fluctuations that became galaxies, of noise that became form. Every photon that reaches us carries a trace of that transition from chaos to complexity. The constancy of this light across time is one of the most humbling facts of existence. No matter where you are in the universe, the CMB surrounds you. Its glow comes from all directions equally. Every observer in every galaxy on every planet sees the same background, the same faint warmth of creation. There is no special vantage point, no centre, no edge. The light defines a shared horizon, a common background for all of reality. It's a universal frame of reference, not for position, but for origin. Everything that exists, everywhere, shares that same backdrop. Even as the universe expands and the galaxies drift farther apart, that background remains uniform. The wavelengths stretch, the energy decreases, but the pattern persists. The photons continue their flight through an ever-growing space, never colliding, never slowing, never ceasing. In the far future, when galaxies have receded so far that their light is redshifted beyond visibility, the CMB will still fill the cosmos. It will be cooler, its wavelength longer, but it will still be there, the last light connecting everything to its beginning. The endurance of this radiation tells us something about time itself. The photons of the CMB travel along the straightest possible paths, following the fabric of space-time as it expands. They don't age in the human sense. They simply exist, moving at the speed of a light, always in motion, always the same. To them, no time passes at all. From their perspective, the moment of release and the moment of detection are the same. They left the early universe and arrived here in what for them is an instant, even though nearly 14 billion years have passed for everything else. The light that never fades also never waits. It moves at the one constant speed that connects all events across all time. That constancy is what allows us to use light as a ruler, a clock, and a mirror. Every photon tells us how much the universe has expanded, how fast it continues to expand, and how its contents have evolved. The redshift of the CMB, the stretching of its wavelength, gives us a direct measure of how much space itself has stretched since recombination. The light records the universe's scale factor in its own frequency. It's the simplest and most elegant measure of cosmic history possible. Light as the record of time's expansion. In the far future, as billions of more years pass, the CMB will keep cooling. Its photons will become radio waves, then longer still, until their energy becomes so small that they blend with the background of quantum fluctuations. But even then, they will not vanish. They will still exist as part of the universe's energy budget. Their wavelengths stretch to such extremes that they define the fabric of the cosmos itself. The universe's last light will not fade. It will become its own background, merging with the vacuum energy that drives expansion. For now, though, the CMB still fills the universe with a warmth we can measure. It's faint but constant, a temperature of 2.725 Kelvin that permeates every point in space. We detect it as static in old radio receivers, as noise in antennas, as the persistent glow that never turns off. That glow is the proof that we live in an expanding universe that had a beginning. It's the simplest, most universal evidence of where everything came from. In its quiet persistence, the light becomes more than a scientific observation. It becomes a reminder of continuity. The photons that began their journey long before there were galaxies are still here, still touching everything. They are part of the same universe we inhabit, part of the same physical reality that includes our own eyes, our instruments, our thoughts. We are not separate from them. We exist within their glow. Every second, those photons pass through us, connecting us directly to the first visible moment of the cosmos. When cosmologists talk about the fate of the universe, they often describe a future where stars burn out, galaxies drift apart, and energy spreads so thin that nothing changes anymore, the so-called heat death. In that distant time, when the universe has expanded to the point where its temperature approaches absolute zero, the CMB will still be there. It will be unimaginably faint, its photons spread across incomprehensible distances, but it will remain the last echo of the beginning. The universe may grow dark to our eyes, but it will never grow completely dark to itself. The light that began it all will still define its background. The persistence of this light also hints at a symmetry that underlies everything. The photons that left the early universe and the ones emitted by stars today obey the same physical laws. Their behaviour is identical, their relationship to time and space unchanging. The universe may evolve, but the equations that describe its light remain constant. The same laws that govern the first second after the Big Bang still govern the way light bends around galaxies or passes through a room. The CMB is a bridge between the ancient and the modern, the extreme and the familiar. In a sense, every light we see is an extension of that first light. The photons emitted by stars, by galaxies, by supernovae are all descendants of the energy released in the Big Bang. The same radiation that once filled the universe uniformly has been recycled, concentrated and re-emitted countless times. When a star shines, it is using energy that originated in the early universe. The cosmic microwave background is the untouched remainder, the part that kept travelling without being absorbed or reprocessed. It's the purest remnant of the first light, the portion that never became part of anything else. If we could somehow see all wavelengths at once, from gamma rays to radio, we would realise that the CMB still dominates. It carries more photons than all other sources combined. Even though it is faint, its sheer abundance makes it the single largest source of radiation in the universe. It outnumbers the light from every star and galaxy by billions to one. The entire visible universe shines against its backdrop, but the backdrop remains brighter in count, if not in intensity. The light that never fades is also the most abundant thing in existence. That abundance connects everything. It means that no region of space is ever truly empty. Even in the vast voids between galaxies, the CMB is there, filling every direction equally. Those photons define the temperature of the universe itself. If you could take a thermometer and measure the heat of the vacuum, you would find that same 2.7 Kelvin everywhere. The universe has a temperature, and it is the temperature of the CMB. It is the measure of the light that fills all things. As the universe continues to expand, this background will stretch, cool, and drift, but it will never disappear. The photons will remain, red-shifting endlessly, their energy approaching zero but never reaching it. The expansion of space will slow their interactions to nothing, but the radiation itself will persist, frozen in time, a silent sea of photons too weak to warm anything but too numerous to vanish. Even in the farthest future imaginable, the universe will still carry this faint hum, this last connection to its beginning. To gaze into that faint radiation is to realize that the universe remembers everything. The photons of the CMB are memory made visible, the record of the first transition from opacity to light, from chaos to order. Everyone that reaches us is a particle of time, an ancient arrival that brings with it the story of creation. The light that never fades doesn't simply illuminate the cosmos. It is the cosmos, still unfolding, still expressing itself in the simplest possible form. And as that light continues to move outward, endlessly stretching with the expansion of space, it carries the same message to every future observer who might one day arise, that the universe began bright, that it remains coherent, that it preserves its memory in the most delicate way imaginable, through the motion of photons that never stop. Each one is a thread in the fabric of space-time weaving together past, present, and future. Wherever you might be, wherever any being might one day exist, the light will still be there, faint, even quieter than now, but still present. It will still carry the same pattern, the same ripples, the same information about the beginning. The cosmic microwave background will always be the universe's first message, still whispering through eternity, still connecting everything that has ever existed. The light that began it all never truly leaves. It simply grows older with the universe, waiting patiently for every eye that will ever open to it. And so, the oldest light continues to move, through galaxies, through empty space, through the expanding silence of time, still carrying the warmth of a moment when the universe first became visible. It has never stopped. It will never stop. It is the one constant presence that unites all of cosmic history. The light that never fades still travels, still glows, still speaks in the quiet language of the beginning, telling the same story to every corner of creation, for as long as there is space to cross and time to exist.